Good morning, everyone. Good morning, everyone. We will be starting in just a couple of minutes, so please take your seats.
Good morning. Good morning, everyone, and welcome. Genuinely, warmly, enthusiastically welcome to SCaiLE, the first event of its kind in EMEA. It is brought to you by TiDB. Look around. You're in the room full of engineers, architects, builders, who got suspicious enough about the phrase Agentic AI suspicious enough to actually show up and investigate. That's a good sign. Smart crowd. My name is Nikita. I'm going to be your host today, which means that I will introduce our amazing speakers today. And before we kick in some things, let me guide you through what's going to happen today. Today we have 10 amazing sessions for you. In all of these sessions, we're going to talk about real experience, how people actually use TiDB, how people actually use our technology to make their companies more successful. We're going to have a few bits from our engineers and developers to tell you what thought process was behind TiDB, how we design our product, what we are thinking about when we are saying that this product is capable to help you in the current era in your business. So, with this being said, don't worry, we got you covered in terms of lunch. We're going to have one lunch break. We're going to have 2 coffee breaks. And you will have enough opportunities to talk to our speakers off stage, ask the questions if you are shy to ask them during the presentation. And we will, at the end of our day, have a fireside panel where you can ask additional questions in terms you were thinking about something but didn't have enough time to investigate more into the topic. Is it clear? Any questions at this point? You can raise your hands. We have quite a cozy company today, so I don't want to be this very formal. And before we start with the first speaker, I want to hand the stage to someone who has been instrumental in making today happen and in building TiDB's presence across the region. Mark leads TiDB's business, which means he has spent a lot of time in rooms like this, listening to what European engineers are going through and delivering this feedback to the internal team to make sure that we're presenting you the very best product. He has a few words for you before we kick things off. So please welcome with me, Mark Hederman.
Thank you, Nick. Everybody hear me okay? It's quite bright here. So for context, Nick just stole my opening speech. So thank you for that. But Nick is correct. The one thing he left out is at the end of today's session, we have food and drinks for networking, other questions, get to know one another. So please stay at the end of that and make sure you get more value from this. But to carry on from where Nick left off, I've been working in the database space for the last 15 years across 3 different database companies. In my 18 months at TiDB, it answered a lot of questions for me. What do we do differently? And you're going to find out today a lot about what we do differently. I've worked for companies that talked about, unlimited scalability, being able to work with multiple data sets, different challenges. We do that in abundance. And one of my proudest takeaways from working with the likes of Ed and the engineering team is we really take on board our customers' feedback and suggestions around problems to fix, product enhancements and new feature requests, and we bring it to market. So today you're going to learn about what we're hearing in the industry across EMEA over the last couple of months from an Agentic AI perspective, and what we're bringing to resolve those challenges. One of our primary speakers, Bernard, back there somewhere, I can see the shine off his head. He will talk a lot about, what he's building, the solutions that are removing a lot of the barriers in the market today. But my 18 months or so here, we have seen significant demand across the region for our services. Some of our biggest partners, the likes of Bold, LHV, and some of the hyperscalers, will talk today about what we do with them, some of the problems that we fixed, and where we're taking them on that journey. And hopefully the messaging you hear today will resonate with the majority of you, and you'll see some similarities in some terms of the challenges that you're faced with. If that does resonate with you, anybody in a white polo shirt, just grab them for a quick coffee, a quick chat, and we're happy to answer any questions. The majority of them are at the back of the room at the moment. A lot of technical nous there as well. So our co-founder and CTO will talk in detail to begin with. We have our field CTO at the back and a lot of our engineers here as well, so you're in good hands. But all I want to do really is thank you for taking the time out from your busy schedules to be here. As Nikita said, it's our first time doing this in EMEA, so it'll be the first of many, and hopefully you get as much value today that we get from it. And I'm happy to answer any questions that you have. I'll hand you back to Nikita. He'll kick off this session. And again, welcome and thank you very much.
Thank you, Mark. All right. Thank you, Mark, again. Right. Let's start where any good conversation about the future of software should start, with someone who has been thinking harder than most of us about the future of this software. Our first speaker is the CTO of PinCap and the co-creator of TiDB. PinCap is the company behind DB. TiDB, by the way. He spent his last decade thinking about what happens when data infrastructure has to keep up with the way software actually behaves, not the way we planned for it to behave. Right? Today he is going to make a bold argument that software is no longer just an application. It is becoming an autonomous system, one that plans, executes, collaborates, and improves on its own. Please welcome on stage our CTO, Ed Huang. Ed.
Thank you. Thank you, Nikita. Hello, everyone. I'm Ed, co-founder and the CTO of TiDB. You know, when, like 12 years ago, when I started to write the first line of code of TiDB, I cannot even imagine what we can have, you know, so many community members here. So actually, it is my second time to be here in Stockholm, this beautiful city. And I'm really glad to, you know, be here and seeing a lot of old friends here. Well, today, as the keynote, I don't want to talk specific, you know, the TiDB use case or technical detail because I believe, you know, just next to my talk, my friend from Bolt will share a lot of TiDB details. Well, today I'm going to talk about something, you know, very high level, because recent days I got a very mixed feeling about the AI and especially AI coding. You know, last year I totally against, you know, to using the because as an engineer I have the proud of being the engineer. You know, I don't want to, you know, use the AI to teach me how to write code. But since last November, you know, everything have changed. I think today, you know, I'm fully, you know, embrace the agentic, not only in the software engineering, but also for all of my, you know, work. So I can see more than, you know, the coding agent as a AI coding tool, but I can see a much bigger paradigm shift. You know, here. So today I'm going to share something, you know, of my own feeling. Okay. Well, first, just like I said, coding is dead. I would say this title is intentionally a little bit provocative. But don't get me wrong. I don't mean that the software engineering disappears. Or the software stop mattering. What I meant is the code itself is no longer the most important part. You know, I speak this sentence as I'm the senior and experienced software engineer. So, but only saying the coding is totally dead. Now the hard part is, you know, delivering the stable and the reliable outcome with the AI in what's importantly in the efficient way. So so I guess there will be a new kind of software in the near future. Well, software, for decades, software was organized around the code. Code as a software engineer, code was what we produced. But in this agent area, everything is changing. I started programming since I was 9 in mid-90s. Started with assembly language. Any of you wrote assembly language, programming language before? Okay. Yeah, everyone, okay. Well, 30 years later, I think I can witness the end of coding, so that's crazy. I'm still young, but yeah. Nowadays, users are increasingly care about the output. Our customers, some enterprise, they don't care about the code anymore. They care about the output and not how it is implemented. For example, when we are using Cloud Code or any other coding agents, we just describe the outcome or describe what we want, and finger crossed. And the AI agent will, magically figure out the rest. In this process, the code, it is not that important. We don't, if we can verify that the outcome is what we really need, we don't even need to take a second look of the code. I don't think that is right, but that is the fact today. I will use the example, to. This product is called DB9. It is my hobby project in last Christmas holiday, just a couple months ago. I always want to try to build a database, new database kernel from scratch with a Postgres interface, because today everyone is talking about Postgres. So yeah. But I want to try. I want to use some complicated project to test the boundary of how the AI coding agent can do today. So I choose the most complicated project I ever known, which is a new database kernel. Okay. Just after 3 months, spending like billions of tokens, and with one, at the beginning, it is totally one-person project. Every day, I basically spend like more than $100 in my coding agent to build this stuff, and then the team is in DB9 team today is only three people. 99% of the code are actually generated by AI. After 3 months, we put this product in production. As a, you can actually use DB9 immediately today on your laptop. And it is quite stable, up and running for near 3 months, supporting tens of thousands online running cluster already. That's crazy. And yeah, this and after this project, I totally, think, hey, myself as a software engineer, maybe will dramatically change. Okay. Well, in the old day, code was the bridge between the user's intent and the durable system. When we have an idea, we hire the engineer to write the code and build a system, and the system produce the result. Well, now with the help of the AI agent, the bridge is being rebuilt. We still need the durable system, but the path from the intent to the result is becoming more automated and dynamic. So that's why I believe in the near future, the agent itself will become the new software. Because in this new model, the agent sits between the user's intent and the live result. The user doesn't necessarily care about how to, build the application, or they don't need to care anything about the intermediate code. The user actually cares the agent can understand the user's requirement, take actions, building the system, and keep the result useful. And my guess is, with the with this pattern, the barrier of to building or creating the system or software is lower. Maybe in the future, everyone would become the software developer because they can just ask the agent to build anything they want. I guess the demand of the software will be exploding. More and more requirements are being fulfilled. And on the other hand, the scale problem does not go away. It becomes even more important in the future. So what we are going to do is we need to prepare the infrastructure for this new kind of software. That's very important. And because today we are not going to build a prototype, or we are not going to build toys, because a lot of users still think the AI agent can only build some toys or prototypes. But what we really need is something we can put in production. But if you want to build something, can put in production, the cost is still very expensive. You still need to host, deploy, care about the security, observability, and the total cost to keep the product or the outcome of the AI alive over time, right? So, okay. When we talk a lot about the agents, and I also guess the agent will be the new software, but now we need to be precise about when we talk about the agent, what does it mean, what the agent actually is. An agent, I would say, it is not only the chatbot or the LLM chat window. Just like ChatGPT is a chatbot, right? I will use a ChatGPT with the OpenCloud as the example. ChatGPT, you ask a question and the ChatGPT will give you, you ask a question, it will give you the answer. But the OpenCloud, when you ask a question or you send it the request, it will, the OpenCloud will give you the outcomes. In the biggest difference from the chat window and the agent is today we give the agent a computer so that they can take actions within the computing environment. So how many of you are using OpenCloud or Hermes? Can you use your hand? Okay, wow, okay. Most of you are using, perfect, okay. Well, this is my definition of the agent, what it really needs. In my definition, there's a runtime. One important component is the runtime itself. It is LLM with the so-called agentic loop. It is not very hard to build. It is just it is a framework that lets LLM decide what to do next in a loop. Okay. Plus the skills. The skills is quite important. It includes the business logic and the rules, how to use the tools, so that that will guide the LLM or the agent to let it use the tools. And of course, environment. Normally people ignore about the environment, but in my experience, the most important part is actually the environment. So, because the environment is where infrastructure become critical. But when we talk about the AI infrastructure or the environment, a lot of people, the first word that comes out in your mind may be the GPU or the the computing power problem today. But I would say in the near future, when the agent become the new software, at that area, what we talk about the agent, it is like you need to maintain millions of agents online to build a platform that operating hundreds of thousands of agents. At that time, that will become the infrastructure problem. We don't have any infrastructure supporting this kind of workload today. So, well, and then we let's zoom in the environment. Let's focus on the infrastructure part. For me, if we want to to see the trend of the infrastructure software or the whole infrastructure industry, the clearest example is take a look at databases. Because I have been building databases for many years. My lesson learned is what happens to the database architecture first often happens to the rest of the infrastructure software later. That means if you can see the trend in database, that means this trend will also happen in the rest of other systems. So let's start it here. Okay. Before we talk about the technology changing, it is important to understand how our customer or the changing from the user side in the area of AI agent. Today, before the AI area, the enterprise always ship with the apps or SaaS platform or software. They're all static application. But nowadays, enterprise, rather than they ship about the application, they start to ship the agents as a service, and then let the agent to fulfill the customer's flexible and dynamic requirement directly. And I will take the Kimi as a great example of this shift. Kimi is a well-known large language model and provided by the very popular AI startup Moonshoot AI. They are, very popular. And their newest Kimi platform offered a new feature that allows a user can simply describe the requirement of a website or the app in plain English, just like Lovable. But unlike Lovable, Kimi 2.6 allowed the not only focus on the front end, but also building the whole backend database and make the deployment and the host the full stack website end to end. That means the outcome or the output, it is not only the source code of the front end. It is a running application with the state. And now we are seeing the next challenge. Code from their official report from the Moonshot AI, their platform creates tens of millions of AI or agent-created applications weekly. Tens of thousands websites weekly. And most of this application requires a database. That means in the traditional infrastructure, you need to provide like millions of Postgres or MySQL instance for this, dynamically created website for the AI generated applications. the cost is unacceptable. So, and by the way, Kimi is actually using TiDB to solve this problem. I will introduce later. And on the other hand, the scalability problem doesn't go away. This is another famous AI startup, very popular. It's called Plot. Any of you are using Plot? Okay, 1, 2. Okay. It is a meeting transcript device. So the AI agent, when you use the device, they will transcript everything. Of course, the Plot is also the TiDB customer. They want to keep a massive amount of transcript data. But with the data set keep growing, but the access pattern was quite screwed. In the AI native workload, everyone will have their own data set. That means in the database world, there's the keyword called the hotspot. But in this kind of workload, it is not hotspot. And on the other hand, their data set have a large amount of data, stay very cold. And most of the queries touch only a very small fraction of the data. So in the traditional data architecture or database architecture, you need to make the trade-off, either to keep everything on the database cluster with expensive storage and pay the cost, or on the other hand, you need to put the different kind of data into different databases to save the cost, but increase the architectural complexity of your system. So, but they are using TiDB to solve this problem in the unified platform. And TiDB originally focused on when we started TiDB as at 12 years ago. At that time, my target was quite simple. Because we are so painful about the MySQL sharding, we just want to build a database that can be an alternative to the traditional sharding architecture, so that we can use the SQL interface more. We don't need to sacrifice a lot of the SQL capability. But nowadays, we are entering the new area of the AI agent. The AI agent will create most of basically the opposite problem. It is not only for the scalable dataset problem, and on the opposite is how do we support millions of tiny databases for millions of agents without turning every database into the real dedicated resource. That means extreme multi-tenancy with scalability. That's a different dimension of the scalability. Okay, so that's why we built TiDB X. It is the new architecture, a next generation of TiDB kernel. We call it TiDB X. So the core idea is it is quite simple. We will open source this new kernel by the end of this year. And now in TiDB Cloud, we already are using TiDB X to serve all the cloud users already. But the TiDB X kernel is built around a very simple idea. The idea is put all the data on object store, which is in AWS, which is S3. So, and then we decoupling the storage from the compute. That means even in the TiKV part, it is stateless. It becomes stateless. Now when you have all the data ultimately lives in S3, the local disk we can free the local disk to provide a low latency path for the active workloads. and the code data will automatically swap to the low-cost object store. And that once you made this architectural shift, S3 become more than a storage, I would say. Today, S3 also acted like a network, and it become the fabric of the system. The benefits is, first, the capacity of the system is basically unlimited. The second benefit is the bandwidth scale with the platform. So, yeah. And from the user perspective or from the agent perspective, and we build this because the compute layer is totally separated. We also make the metadata system separated from the PD in the TiDB X architecture. So we basically rebuild our metadata system and to build a virtualization layer on top of the SQL layer. That means from the user or the agent's perspective, it looks like every agent has its own isolated database. But from the platform side, it still uses a shared, the infrastructure. And so on the top of the KV, key value part, we redesigned and we introduced the concept we call the virtual database. So that's how we solve this the millions of isolated database problems for the customer like Kimi. Well, this is not just about the bigger scale. It is different kind of scale. Long tail tenant, mutable schema for every different customer, bursty traffic. And the logical isolation. Traditional approach like, for example, prepare Postgres per tenant or schema per tenant will hit the cost issue. Well, the agent workload maybe needs something like this. And I would say, let's take one step further. The database story is not unique. The same pattern is emerging across the agent infrastructure stack. Today, if you want, more and more customers are started building their agent platform. The agent needs, just like I said, agent needs a computer. Agent needs compute, agent needs storage of that computer, they need database, they need environments. And the most straightforward approach is just simply give every agent their own, the complete environment that minimize the friction, right? So, but let's think about it. If you give every agent the full environment, the cost problem will come back. So, and at a massive scale, that becomes impossible to ignore. So, remember how we solved the database scalable or the multi-tenancy problem for agent. Let's use the same pattern to take one step further. If the agent needs a database virtualization like TiDB X, they will also need the same principle across the whole environment. Like I said, the sandbox, file system, network, and their whole life cycle. So, in the TiDB X pattern, I call it virtualize the interface. In the interface side, every user, every tenant will think they own the whole database, but it's a virtual database. But share the infrastructure underneath. If this works for the database, just like I said, the same idea, I guess, should apply to other components. And the platform will pay only for the real usage. And in this pattern works for the agent because, imagine you are using OpenCloud or Cloud Code or any other agent. Agent only works when you have a specific message or specific task to send to the agent. In my observation, near 99% of the time, your agent is actually being idle. But if you give the whole environment to the specific agent, that means 99% of the infra cost will be wasted. So this approach, I call it the serverless principle. From the agent view, the environment should always be available, and the state should always there. But from the platform view, the compute is elastic, and if you can provide this scale to 0 when idle, that will be save a lot of cost of the whole platform. So the idea behind that is quite simple, because I think always on does not mean always running. That's the key principle. In the future, if I build any infrastructure system, I will always use this principle. Always on does not mean always running. So we can only keep the endpoint and the state remain available, but the compute, which is actually really costs a lot of money, only appears when they need it. Okay, so I use this idea to build a research project to use this the principle to not only building the database environment, but I want to build a complete serverless environment infra for the agents. I call it CEST. It is a research project in PingCap. The goal is quite simple. For one agent, one whole serverless environment, and that environment can scale to millions. For example, you can use like limited hardware resource to create like millions of agents online. So this is what we call the agentic cloud. Yeah. So this is the front page of CEST. We build all the necessary component in the composable way. Like Run9 is a sandbox service, DB9 is the database, Off9 is observability platform, Drive9 is a distributed file system you can easily attach to the sandbox. The Smith9 is a reverse proxy or the message gateway for the agents. Yeah, we do a lot of components in the with a Unix philosophy. The 9 is actually comes from Plan 9. This it's old Bell's Lab operating system, which is my I would say favorite operating system with a really good taste. So I use this name to make a tribute to Plan 9. Okay, this is what CEST9 includes. So you can take a look. Okay, this is the last page. This principle behind all of this, from the user, I think in the future, they can be free from, the infra problems, like about, where the agent environment is, where the agent, how many agents behind the scene, how the state is stored, which database I'm going to choose, how the idle cost is controlled. This is all the infra problem. I don't want our users in the future care about all of these, infra crash problems. The agent and the user should focus on the business logic, and also the outcome. Our job is to make the agent environment simple and friendly and economical enough for all the complexity, disappears behind the platform. So that's our vision in CEST9. Okay, back to the opening. Coding is dead, but software isn't. I think with the right platform support like TiDB X and the CEST9, we may enter the new golden age of software. Thank you. Yeah.
Thank you, Ed.
Okay.
That was beautiful.
Yeah.
Yeah. Starting coding from the age of 9 and still going, vibe coding. How many of you have kids? I have 2. Oh, a lot of you, right? And I was thinking about it, how I'm going to explain to my kids, my oldest one is 5, that we actually had to type in some code instead of just communicating directly with some kind of a ChatGPT or another agent, right? Because what we were doing last week with my 5-year-old son, I told him, you can imagine any game, anything that you want on a screen. And my 5-year-old was dictating something for 30 seconds. And then 2 minutes later, there was a colorful dinosaur popping out and doing some stuff, something that I would have spent, I don't know, maybe a week, maybe a month even to develop. So yeah, this is crazy. And that's our reality. And that's a good example of people who are actually standing behind our product, right? With the passion, with the dedication. No matter what happens in the world, we are still continuing and doing our best to give the best tools to our customers, to you guys, right? But enough about ourselves, about our company, about our philosophy. Let's switch to real case scenarios, right? How many of you have used Bolt this year? Like taxi drive, right? Well, statistically, we're in Europe. We all used Bolt at some stage, right? But Leandro, who is going to talk today about his journey, he is responsible for database systems behind the hood. And I'm sure you have never thought about database systems when you were ordering a Bolt or delivery food or something like this. And this is exactly how the systems should work, right? Smoothly, that you don't even think about them. Now, after pandemic, Bolt saw a significant growth, 400%, more than 100 million users, more than 500 countries across the globe. And what started with a pretty outdated, let's be honest, MySQL database, soon it showed that it needs to be leveled up. And that's how Bolt decided to first try TiDB, and then, what then Leandro is going to talk about right now. Leandro? And you didn't know this. This is a surprise for you. But Leandro, not only a very nice-looking guy, not only a very clever guy, but he also one of our biggest contributor into our community. And that's why, Leandro, we would like to use this opportunity to give you a little something from our side.
Okay. Wow. Congratulations, and thank you for your, I think,
Thanks.
Community is really, really important for TiDB. And Leander, you are the, I would say one of the most important people building this, TiDB momentum in Europe. Yeah, I want to take this opportunity to send you the small gift, also from our TiDB user, which is it is a proud note taker.
Awesome.
Yeah,
Thank you.
yeah.
I wasn't expecting. Thanks,
Thank
Ed.
you.
I'm glad to talk about TiDB.
Yeah. Thank you.
Thank you. It's made my life much easier, and I want to share this with everyone.
Yeah,
so,
and powered by TiDB.
awesome.
Yes,
Thanks.
thank you.
Okay,
Thank you.
that's a good way
Yeah.
to start a talk. So awesome.
Yeah.
Can I have the
Yeah,
clicker?
here is your clicker.
Okay.
Thank you. The stage is yours.
Great. Thank you. All right. Let's just give the tech guys a second to. Okay, here we go. Good morning, Stockholm. Good to see you all here. I'm Leandro. I'm from Portugal, and I'm do the databases at Bolt. So today I'm going to be talking a little bit about our journey from MySQL into TiDB, what problems it solved, difficulties that we've had, and basically where we stand right now with TiDB usage. Yeah, the agenda is pretty self-explanatory, so let's move on. You probably all know Bolt. In case you don't, we're one of the fastest growing tech companies in the world. We have over 200 million users. You probably saw in the talk description that it said 100 million, but we're now at 200, so you can get an idea of our growth from that. We operate in these many countries, mostly Europe and Africa, but we're also expanding out towards other continents. So our operation is quickly becoming worldwide. And what we do, if you're not familiar, we're mainly a ride-hailing company. That's the core of our business. But also we have micromobility, which is rentals of electric scooters and electrical bicycles. We have delivery of food and groceries. And the last vertical, Bolt Drive, it's basically you can rent a car through your phone in an easy way for a few hours. So it takes the hassle out of car rental. So how do people interact with Bolt? It's mostly through the app. You might have used it. This app is developed by hundreds of our developers. We run a microservices architecture, and our business activity generates a lot of data, hundreds of terabytes of data. Everything's running on AWS, and all this data is fed through Kafka to our business analytic data lake for business intelligence. So looking at the actual database stack that supports this business, this is not our whole stack. We have other components, but in terms of database, these are the main ones. Our application sends traffic to the database backends through proxy SQL. It's a very flexible routing system. It allows us to do query mirroring and a bunch of other cool stuff. And traditionally, we're running on MySQL asynchronous replication, one master and multiple replicas. And we don't have that much of MySQL anymore, as we've been migrating to TiDB over the last 3-4 years. I'll tell you the reasons in the upcoming slides. As I mentioned, all the data goes to our data lake through Kafka. With MySQL, you feed that through the Bezium, which does change data capture. And in TiDB, there's a drop-in replacement called TiCDC, which does that function. In terms of infrastructure, MySQL is running on, everything's running on EC2. We self-manage the whole infrastructure. MySQL is x86, whereas TiDB runs on ARM for cost reasons and performance reasons. And in terms of provisioning, we do standard SRE practices with infrastructure as code running Terraform for deployment, Ansible for configuration. And we have a bunch of tools for migrations, backups, etc., that we write internally with Python and Go. So going to the core of this talk, why did we feel the need to move away from MySQL? So the main reason is, as I mentioned, growth. The company is growing a lot. It's a good thing to have as a business. It means you're making more money, you're serving more people, but it does bring about some challenges for your technical teams. Your database team needs to scale up and accompany this growth, and needs to make sure that your query latency stays stable and the whole thing just doesn't fall apart. Problems we've had with MySQL as we started to grow is it's not really designed for large scale. So once our tables started hitting more than a terabyte, we started to see slowdowns. For example, in backups, our RPO or RTO times, basically the time it takes to do backups and restore, started to increase. It puts the business at risk, creates a little bit of anxiety in your teams. And even if you, for example, we back up to S3, which is highly scalable, but the bottleneck is MySQL being a single instance. So it's still like one-threaded. You can't really parallelize that. Another big factor that was slowing us down was online DDLs. So our developers release many features per day. We have dozens of changes that we need to make on our tables every day. And once the tables are large, MySQL starts to struggle a bit. We use a common known tool called Ghost for online changes on the database so that MySQL doesn't block. And this process means that you have to make a copy of the table and then you have to delete it, right? so that you get an idea to change a 1 terabyte table on a loaded cluster. It'll take us about a week. And the worst thing is that you can only run one change per cluster, which means that every other user in that cluster that wants to make changes is piling up behind this change that's taking a week. So your developers start to become a little bit angry, and developer velocity slows down, right? Other bad things is Ghost actually makes a copy of your data. It creates a shadow table while it's doing the modifications. So say you have a 5 terabyte table that you want to change, it means you need to have another 5 terabytes free just to do that one change, right? And at the end of it, you need to drop this table. And I'm not sure if anybody has tried dropping 5 terabyte tables in MySQL, but InnoDB kind of stalls and freezes. So that would cause you a little bit of downtime. And in general, it's just not a very fun process at scale. So that was one of our key pain points with MySQL. Another thing that we have with InnoDB, if you delete data and you want to reclaim the space, you need to rebuild the table, you need to optimize the table. So that means that you also need that much free space, and it blocks the writes. So these were the main reasons in terms of MySQL data size. The other thing that you get with growth is more workload, more QPSs, more things hitting the database, right? Which again is good, but it brings about challenges. In terms of reads, with MySQL it's not so problematic because you have asynchronous replications and you can just add read replicas to scale out your reads. But write scaling is another story. Mainly because MySQL is single instance, and if you want to increase capacity for writing, your only option is to scale vertically. In other words, you have to give it beefier hardware, increase your instance types, and the problem with that is eventually you're going to reach a limit. There's no bigger instances, so what happens then? Does your business stop? And the other thing is, as you increase instance size, the cost goes up, but it's not in line with the performance. So sometimes you pay triple the price for double the performance. So that's not very good for costs also. And also, when you're scaling out with MySQL, since it's a single master, you need to do switchovers, master switchovers. So it's not very flexible there. How do people usually get around this write scaling limitations? So they usually adapt this divide and conquer strategy, or in other words, they'll use sharding, which is breaking up your databases into smaller pieces, and then you can parallelize your writes, okay? The problem with that is that it's heavy on management. Now you need to figure out where your data lives, how to join cross-shard queries. It's quite a complex logic to manage all of that. Many companies, they think they can put this in the application level, and some do, but again, it's complex, and your developers don't really want to be doing sharding logic in their code. They want to be releasing features. They don't want to be managing your data. So essentially, it becomes a very specific project that developers don't really want to own. So to get around this sharding logic in your application level, there are other options. One common one is to put a proxy in front of your MySQL database, the backends, and this proxy will be responsible for doing sharding. And lastly, the option that we adopted, and many people do, is moving to natively distributed databases where the sharding is actually done at the database level and it's transparent for the DB users. So that's how you mitigate write scaling. In terms of high availability, as I mentioned, MySQL is single master. If your master goes down, you need to do some failover. During the failover, you'll have downtime. Even if you have auto failover, for example, there's a MySQL orchestrated tool that does this failover for you, you'll still get some hiccups and people will notice. Additionally, this failover is needed every time you want to scale up, switch masters. And overall, it's not very durable. No, it's not very available. In terms of storage costs, every time you add a replica to MySQL, you have to have a full copy of your data. And often you need replicas not just for read scaling, but for example, you might need to do backups on a replica. You don't want to do them on your master. So there's another copy of the data. We have binlog servers to feed Kafka. There's another replica. So every time you need to add one, you have your full data copied across, so costs are going to increase. And also, there's no, so your data gets stale. We don't need ride-hailing information from 10 years ago. Your tables are just going to grow. But the developers don't really care. They're just worried about doing their services. So what happens is you need some external tooling to do data archiving and data cleaning to keep your tables lean. With MySQL, you need external tools like PT Archiver, and often it's a forgotten thing until the tables get too large. The last thing is data compression. It is available on MySQL and InnoDB, but you have to explicitly enable it. And many times it's just something that people think about later on, once you have large data. So compressing it is going to imply rebuilding your tables, etc. So it's not automatic, so to speak. So these are the reasons why we felt the need to move away from MySQL, and we started looking for alternatives. We run a MySQL shop. All our code is MySQL based. So even though Yugabyte and Cockroach are natively distributed databases, they speak the Postgres protocol and they're not really compatible with MySQL. So adapting all our code base for that would mean a big effort, a big rewrite, and it's not a engineering cost that we were looking forward to. So that left us with Vitess and TiDB. The first time I looked at TiDB was, I think, version 3, or it was very early days, and we didn't feel it was mature enough to run at our production level. So we looked at Vitess, which was used at YouTube, it was used at Slack. Now Vitess is one of those sharding proxies in front of MySQL, and we did a POC. We actually ran it in production for a while. But after a few months, we decided to move away from it for a bunch of reasons. For example, it didn't support MySQL style grant and revokes. There would be problems with DDL where one shard would finish the DDL, the other shard would not finish, and we have out of sync shards. We needed to manually rebalance our shard data. So yeah, after some time, we decided it's not really working out. By that time, TiDB had increased a few versions. It was in version 5. It was more stable. Documentation was there. And we decided to give TiDB another shot. So yeah, we did a POC for TiDB, and I'll tell you later about the migration. But the reasons why we chose TiDB over other solutions is, again, it's a natively distributed database. What does this mean? It means that TiDB will actually split the data into multiple, they're called regions, don't confuse them with AWS regions, but basically it's small shards that will live in your TiKV storage instances. These shards or regions will be replicated using the Raft protocol, and they'll be highly available. Usually the replication factor is 3. You can put it up if you want. But they'll be highly available, highly replicated on your TiKV storages. And also storage and compute is decoupled. So if you have these TiDB nodes which will process your application SQL queries. They'll do the query optimization, query planning, and then when they need storage, they'll go to TiKV. So often we need more compute power, but we have enough storage. With MySQL, you had to increase the whole instance, so we'd have spare capacity in terms of storage. With TiDB, it's very flexible, and we can scale up, well, scale out, basically, each component individually. Also, as I mentioned, it does the sharding for you. The developers don't need to worry about specifying, either managing keys or, in the case of Vitesse, specifying sharding keys and knowing how their data is split. That was the main reason for choosing TiDB. But there were other factors that we needed to have to implement it. The main thing was MySQL compatibility. As I mentioned, we don't really want to change all our code base to change the database, and I don't think our devs would buy into that. So yes, there are a few incompatibilities, mainly around auto increments, some character sets, but it's been improving. Like when we started, we couldn't migrate from 8.0. It only supported MySQL 5.7, but now you can migrate from 8.0 instances. Also, since we were going to be doing a lot of migrations, it needed to be easy to copy the data from MySQL to TiDB, and there's migration tools built in to TiDB, like DM Data Migrator and Lightning, that allows you to do this. Also, I mentioned we feed all our data to Kafka, and if that pipeline didn't exist, it would be a showstopper. So with TiDB, there's native TiCDC export of data to Kafka that allows us to continue and get the buy-in from the data lake team. The other thing that we wanted to solve was this online DDL to not have developer velocity hindered, and also with increasing scale, backup and restore is done with BR tool in a parallel way. If you remember the TiKV, this slide here, the backup can read, like in this case, it can read from 9 TiKV nodes in parallel, so backup speeds are quite high. Okay, finally, in terms of monitoring, for example, with Vitesse, it did have collectors for data, but it didn't have any Grafana, no alerting. We had to build that all ourselves. Whereas with TiDB, it has a TiDB dashboard and Grafana panels built in. So all the monitoring and the alerting is already built. You don't have to do it yourself, and it allows you to operate the database with ease. Some features of, other features of why we chose TiDB, high availability. So TiDB is multi-master. It means you can write to any DB node, and it'll do the conflict resolution itself. So if one TiDB node goes down, the rest will keep on serving traffic. Same thing happens with TiKB. We've had instances where our AWS instance has failed. You see a little blip in latency, like 2-second, 3-second spike, and then it auto-recovers, and it's business as usual. So you don't actually get a downtime or an outage. You do see a little latency spike. So the application retries and everything's fine. In terms of storage, TiDB does compression transparently at the TiKV level, and we've seen 2-3 times. It depends on your data, obviously, how compressible it is. But we've seen 2 to 3 times storage compression. So it allows us to reduce costs for storage nearly 50%. For deployment, okay, since we do run TiDB on EC2 instances, we use TiUp. You can run it on Kubernetes with operators, but we're still running on EC2. And this TiUp tool allows you to manage your cluster very simply by running one command. You can scale it up, scale it down, deploy it. So in terms of operations, it's very simple to do. With MySQL, we had Ansible scripts to create replicas, do the setup, etc. TiDB makes that quite easy. And in terms of development, okay, so developers need a way to test the database easily on the laptop. And with TiUp Playground, you install one command, you run it, and you have a TiDB cluster up in your laptop ready to use. It's quite flexible. You can specify the number of TiKV nodes, number of TiFlash nodes. So it's really powerful for testing. And finally, in terms of support, it's always good to have somebody to help you in case you're stuck, especially if you're running a production database at our level. So we have a contract with support from PingCap, and they'll help us. We found a bunch of bugs so far that we've reported to PingCap, and they've been fixed in upcoming versions. And even in terms of, for example, if something is urgent, we'll get a hotfix patch delivered to us that we can apply in production so it doesn't bring things down. More bonuses is documentation is actually quite good, very extensive, and it's open source. So these are all wins for using TiDB. So we finally decided, okay, let's go ahead, let's do TiDB. And our very first migration was actually from Vitesse. Nowadays, we don't run Vitesse. We only have this cluster. We do all our migrations from MySQL. But the process is basically the same. You have your TiDB target cluster here, your MySQL environment up the top. You use this DM data migrator to copy the data and start replication. So all your writes from MySQL are replicated in TiDB, and you have the same data. And basically, once you're ready for migration, you switch the traffic at the proxy SQL level, and it starts writing into TiDB. In terms of feeding stuff into Kafka, you have the Bezium connector for MySQL or TiCDC for TiDB. In this case below, since this was our very first migration, we decided to have a plan B fallback in case we needed to go back to MySQL. We've never needed to use this fallback plan. So our migration process, basically for each schema, we migrate per schema. Our devs will spin up TiDB playgrounds and test in the local environment. Then we do a migration in our staging TiDB cluster that we have. They'll evaluate it again. And once they're confident, we'll proceed to the live production migration, okay? So once the system is up and ready, the data is in sync, we don't migrate right away. We do a little bit of load testing, so to speak. So what we do is we use proxy SQL to do query mirroring from MySQL into TiDB, and then we observe those queries in TiDB, the latencies. We see if there's any bad query plans, so we have an opportunity to fix it before doing the migration. Only once we're confident that TiDB is going to execute everything with the same performance as MySQL do we actually do the live switch. We have a tool called DB Migrator that does this switch in a few seconds. Yes, there'll be about 10, 20 seconds where writes will be stopped, reads will be continuing, but yeah, that's the price you have to pay for migrating. What the tool does is it copies the users, the database users, into TiDB, kills the connections on MySQL, changes proxy SQL, and traffic starts going into TiDB. The last step is actually switching our source for Kafka from the Bezium to TiCDC and monitoring performance and doing the cleanup of the schema on the MySQL cluster. So these are some of the benefits that we've gained post-migration. As I mentioned, I'm probably not going to go over all of them because you can read. But if you look here at the alter table, this was adding an index on a over 1 terabyte table. And this is the thing that would take us over a week in MySQL. You can see here that it took us 22 minutes to do it on TiDB. And this has actually been increasing. In earlier versions, it could have taken like a few hours. TiDB has been improving, and if you see this DXF feature in the bottom, it stands for Distributed Execution Framework. So that makes add index even quicker. For the backup, here's another example. We backed up 60 terabytes in an hour and 15, and after compression in S3, it took up 15 terabytes of data. So this allows us to run our operations at scale. Some of the features that I want to highlight is more around these ones. TTL is what I told you that it's automatic data archiving for your tables. When you create the table, you can just say archive anything older than 1 month or 1 year, and there'll be background processes in TiDB cleaning that data up. Flashback is really useful utility. Has anybody done like drop table or delete without aware and only realized after pressing enter? What this does, it allows you to roll back to a previous state. We've actually had a recent case where during a migration, we forgot to kill the replication from MySQL to TiDB. And we were cleaning up the schema in MySQL, so we dropped schema, and it got replicated to TiDB. Like, things started buzzing and flashing. So this flashback schema was really useful. We were able to get everything back in 2-3 minutes, and it basically saved our butt. So that was a really good feature to have. The final thing, SQL plan bindings. It can happen that some dev will release some feature on Friday and then go off on holidays, and their query is really bad and is putting a lot of load in the cluster because it's choosing the wrong index, it's doing full table scan, whatever, and you don't have contact with them for them to fix their query. So what you can do is you can actually force TiDB to use a specific query plan, specific index, without touching the code base. So it's not something that you want to use has a standard procedure because your query rules will start piling up, but it's very good in emergency situations where you want to fix things quickly and transparently. Where are we now? So 90% of our schemas are on TiDB. All our new microservices, all our new databases go into TiDB, and it's a default database. We are implementing some features still. It's work in progress. Resource controls basically allows your databases to be limited in terms of how much resources they use so they don't starve out the rest of the cluster. Table partitioning, we have a case, for example, where tables like 15 terabytes, and sometimes we want to drop old data. So even with TTL, it can get expensive and slow. So we're looking into partitioning that table itself. It's basically sharding inside sharding. So so that you can just drop an old partition that has old table. Also, excuse me. Also, the TiCDC, there's a new TiCDC architecture. The old one had some issues where change feeds that were very large would start to lag. And it worked, but it wasn't very scalable. So Pink implemented a new TiCDC architecture, which is event-based, and we're testing that out. It's still work in progress. And finally, we're in the middle of doing upgrades to 8.5.6, the latest GA version. It's so far going quite well. We've done about half. And benefits we've had is less bugs, more stable. Query latencies have dropped about 5 to 10%. So with that, I want to leave you with this last slide here. This is our upgrade history. We started on 5.4, we're on 8.5.6, nearly done. So in conclusion, TiDB has really been a lifesaver for us. It's allowed us to scale, run the business without as much problems as we had before. And in general, I just sleep better running this than MySQL. So I hope you enjoyed the talk. If you have any questions, feel free to come and ask, even after the talk. So thank you.
Thank you, Leandro. Beautiful talk.
Cheers.
We didn't bribe you before that to say nice things about us.
No,
Right?
no.
I just want you to say this out loud.
Yeah.
Right?
Okay.
Yeah. That's a real experience.
Can I
Thank
go?
you. Thank you
Okay,
again. Don't
cool.
forget your
Yeah.
prize.
Yes. Yeah. Nice. Thanks, Ed.
All right. So now we had the real experience, the real story. Let's go back to the idea behind TiDB. And our next speaker is Matthias. Matthias is a principal software engineer at TiDB. which means that he is actually the one who is responsible to deliver all the promises that our marketing and sales guys are making, which is not an easy job, as you can imagine. And Matthias is going to talk about the topic that I think we're facing to some extent on a daily basis, especially when we're designing, when we're developing new systems. It is this urge to add a new system whenever we are facing a new problem. So we want to add a vector search, we are adding a vector database. We want to add analytic, we are adding warehouses. And Matthias states that it is not actually necessary. The one thing that you actually need is to have a reliable database with vector capabilities. And Matthias is going to talk about it more in details. Matthias?
Thank you. I'm Matthias. I've been at PingCap a bit more than 5 years now, doing TiDB, working mostly in the SQL layer and coding and so on. That's my day job. And then my extra curriculum is more or less coming like this, meeting customers, explaining more what the technology is and how it works, and also listening to customer, how we can actually help solving your problems instead of just producing tech that's for tech's sake. So I'm here to talk about vector search meets distributed SQL and why Agentic AI don't need another database. When you do an AI platform, you usually already have some systems, most likely relational database. You might even have a document store, or you might need adding a document store for scaling writes or saving a lot of objects or documents and so on as well. You might do retrieved augmented generations or RAG. Then it's common to have like a knowledge graph or something like that. So you would throw in a graph database because that's what you do when you do it right for relational reason. Did I say relational, by the way? Didn't I have a relational database already? Well, you can actually do the relational graphs and the knowledge graphs already in a relational database. And then, of course, vector databases, because that's what provides similarity search or semantic search, which is actually a strong core of the whole AI foundation, how you can find things that in images or text or documents or anything like that, because computers are really good in comparing things, right? But if it has no clue what things are, then how would you actually compare it? And that's more or less where vector databases comes in. The thing is that when you then compile all this stack and different things, you do have more or less the same data in them or parts of the same data in all the different systems, which means that you have to insert them or ingest them in different ways because they are different systems. You need to keep them in sync, because if you're going to query all these different systems, you want to have the same answer, right? You don't want to have something that includes the update you just did and something that doesn't. You want to have a consistent view of this, right? So it's not only 4 systems you most likely even have 8 systems, right? And that really leads to the first part here, the data sync hell. So how do you even keep this data in sync? You have multiple systems. You need to sync them, keep them in sync. Probably you have some kind of brittle ETL, so extract, transform, load. And it's all different between the systems. You most likely even remove data or even add data or decompose it or anything like that. Then you also do have the operation burden, because each system needs their own expertise for running it. 4 different systems means that you have either more knowledgeable people operating it, or you have more teams operating it. As well as then, how did you keep it in sync now again? Well, that's yet other people that will need to do that, right? And as soon as you change one of the system, the pipeline might change, so that just follows up with the other systems as well. So it's a lot of other burden that you need to do. And that all means that it's spiraling total cost of ownership, right? So it's licensing, infra, ops, and then it multiplies by the more system you add. As well as for developers, and how do you actually do this? Well, I would say it's more like schizophrenia, right? It's like developer decision paralysis. So which system do I actually go to query my data? Where do I get this? If I need to update this, where do I update it? How do I keep it in sync? So that's quite a Frankenstein or Frankenstack, I would say. A bit back to vector databases. Everyone knows what a vector database is, what vector embedding, how that works? Okay, anyone? I'll go into it a bit then. So a vector, you can see it as a meaning or an intent, but it's encoded in numbers. Computer can do numbers, right? That's easy to compare and so on. So you take some kind of object. Here I do have a small text, like a small dog. And then you have an embedding model. It's similar to what an LLM does. It takes some input and generates some output. The output is always in the same format. So when you specify which model you want to use, the output will always look the same. OpenAI's embedding models comes up to 3,000 dimensions, actually. So 3,000 different floating point values. And every output would have these 3,000. So it's very easy to compare because it's the same format of it. And you can see that if you would compare it with a one line or one dimension, two dimension, then it's easy to see where it would come, and you can compare how close they are. And that's really what the similarity would be. For example, if you would just use text instead, in academia or something like that, some person that is a bit more formal might say, like, which automobile has the highest velocity? Well, you would just really say, which car is fastest? It's the same meaning, right? But let a computer compare them, it doesn't match at all, right? But it should. That's what you use the vectors for. And you can even do it in SQL, actually. So in this case, you just do a normal select. The important part here is that you order by the distances. So here I do have one of the more common, you use a cosine distance. I'll share a bit more about that. And then you compare that with all the different embeddings from all the other rows with the one you had in your question, basically. So you compare the question to all the different possible answers, and then you would find which answer is the closest to the question. And then here you would get like small dog, puppy, small terrier, beagle pup, golden retriever, etc. So this is one of the core features of the AI backend, really, to map from a question or a document or something like that to get more context out of it. And this is more like representation of that. There will actually be even better explanation of this by Silish, by Simon, in the afternoon. So I won't talk too much about that. But to do this comparison with 3,000 dimensions, computers are quite fast, right? So 3,000 numbers, that should be fairly easy. And if you have a handful of rows, that's still manageable. But imagine you have 1 million rows. In my world, 1 million rows is a small database. A large database has at least 1 billion rows, right? 1 billion times 3,000, that needs to be compared, and finding something, that's really, really, really hard. It takes enormous amount of capacity or time to actually compute, and means it's expensive. So what would you really do then? You would actually have an index on it. And the one here, how would you index data like this? Not this either. You can't. You can't do an exact index over this. So there are other ways to do it. If you would do an exact index of this, it would be extremely expensive as well. But there are algorithms that can do approximation, so approximate nearest neighbors. Then you can actually do an index over this in a subsystem or in your database or something like that. The approximation means that you might not get the full hit. There might be some elements that are not there, or you might get the 6th instead of the 4th, for example, in this. But it means that you can actually do it efficiently, even over 1 billion rows. So what if your SQL database then could do this? The data already is in your SQL database, right? Because that's normally where you have the production data from the beginning. So what if vectors live there too? Well, it would be a single write. It's only one system. So one store, no sync, all the pipelines. There's no pipelines, it's just a single system. It's one language. You don't need to do graph database language, which is very specific. Vector databases don't do direct SQL either, normally. You do have the document store where you also do more or less your own query plan and so on and so forth. You don't need to do anything else than a single connection. You can even do this in a single query. And with all the different systems, you need to do all the glue work as well, right? You do need to go to one database to get one system to get the result there, then go to the next to enhance it or add the data you're missing and so on. It's always fresh. It's the same data. You don't need to sync it. And full text search might also be in the database. You might have even more functionalities in the database already. So SQL that solved all this, because you shouldn't need to be the query planner. If you go and ask more or less anyone that works on databases, especially SQL databases and so on, which is the hardest part of the database to implement? Anyone would take a guess? It's a query optimizer. The joke among the optimizer folks is like, well, if you flunk the database optimizer course, that's when we send you to rocket science. So with SQL, what you actually do, you're asking for the result. You're not telling it how to extract the results. So it can do the optimization of the query, so it has the execution plan, it executes, it combines data, it ranks it, and everything like that. And it will do it on consistent set of data. So that's all where the transaction part comes in as well. If you would do it in the Frankenstack, yeah, you transform, you write it to all these different systems. You need to figure out which system to start, how to querying it, how to get the results, how to stitch it together with other results from the other machines. Can you do it in parallel? Do you need it to do it sequential? And it's all out of sync, so how do you handle the corner cases where the data might not be there in one of the systems? Yeah. The Frankenstack is really a regression, I would say. This you've seen already twice in different format actually today. I'll go slightly through this. This is what TiDB looks like. From me, more like how we would arrange the code, what it would produce. I mostly work in the SQL layer. I've been doing table partitioning. I worked on that already at MySQL for several years, and now I did even global indexes in TiDB and done something of that. Now I'm working a bit more with statistics for the optimizer. But that's where the SQL processing comes. Then it has a row store. That's the normal transactional database store. That's where a row store lives. That's where normal indexes lives and so on. This is kept in sync over a raft protocol. So we, as Leandro said, we by default store 3 copies of the same data in the row store. while we was doing that and refined it and so on, we had questions that, I only do more analytics load and so on. Is there a way we can speed that up? And we figured out that we already have the data stream of all the changes through the raft protocol. We can actually use that directly to feed a columnar store. So we actually can have a consistent view of the data in a columnar store as well. So you can scan 1 billion rows for a single column in no time, basically. Great for aggregations or scanning when an index doesn't match and so on. And through the same raft protocol, we can actually feed a vector index like the approximative index, because that is not per row, really. It's like a subsystem itself doing the indexes, similar with the full text index. So all this is kept in sync. And the SQL layer is smart enough to know which part to use in a single query. You don't need to send parts of this or tag, oh, I want to use the columnar store for this or use the vector index for that. That's how it would work. And then we actually do have the object store. It's the latest edition, I will say, as a source of truth, unlimited bandwidth that Ed talked about. In TiDB X, so that's our 10th generation, our cloud service, you can more or less group from the other picture more of a service-oriented architecture or microservices, where you do have query processing and so on the top, a bit of the data engine, storage engine, and all this is based on the object store. So the row engine and column engine, you can see it as it caches back the active data and leaves the cold data in the object store. But it also means that we can have a service layer that's not in the hot path of querying. For example, we're using a log structure merge tree for the row store that needs to do compaction for keeping it up to date, to remove all data and so on. We can do that without hitting the production part or the querying serving part. As well as before, without the object store, we need to do that in all of the 3 copies. Now we can do it once and cache back the results. We can also do alter table, just like Leandro said, that you can do that more or less off the production load. That also reads directly from the object store and writes it directly to the object store, and then just provides it directly for new queries when the index is done. And that's nodes, that's services that's only needed when you're actually running alter table. Same with analyze table and so on. So the TiDB X, our new generation, a 10th generation cloud service, it's extremely efficient, actually. We have customers that I think they cut the cost from going on the old generation to the new one by half, while getting more performance out of it and lower latency. It also means we can scale to 0 and a few other things like that. If there's any question, I do have time now, or we can just discuss it later on, then I have even more time, of course. This all means that we can also serve Agentic AI, because now we do have all the different components. It's slightly a bit about memory for agents and so on, because Bernard will go much, much deeper into that. One thing that I haven't mentioned is that we can actually do branching. So you can actually do a full copy of the data and give that to a new agent. It's more or less 0 cost, which means that you can experiment and test on actual production data, and you can write to it without affecting production. It's really nice to do both for humans and Agentic AI as well. And all this means that for the business, it's time to market, right? It shrinks. You can be much more agile, you can iterate much, much faster. And for engineers, the production data is still safe, while you can actually try everything. You don't need to have like an extracted small sample of the data or out-of-date things, or need to massage the data just for running it. You can actually get a full copy, play with it, throw it away if you want. So where are we heading then? I would say that we are going more and more to the cloud. So what you want is a cloud-native database like TiDB, and the object store will become more or less the network, as Ed said, or the source of truth, because it's actually an amazing piece of software. And all this makes the Agentic AI extremely affordable, and you can dispose it, you can run it just like you want. You can spin up temporary things, you can actually run things and keep the history. It's up to your use case, right? So the future, it's not a database plus AI stack or more systems. It's using a single system to do more instead. So your SQL database can speak vectors and scales and do full text search and all the things that Agentic AI really needs. So for Agentic AI, that means that it's one source of truth, it's fresh, consistent, and with no extra system or sync hell. So I would just say, go with TiDB.
Just want to make sure that you're done with the slides. Thank you,
Yeah.
Matthias. Beautiful presentation. I like the visualization, almost like, what was it, Plants versus Zombies. Something like this. Okay, our next session is gonna come from one of the most technologically advanced banks in Europe. But before that, I propose we take a break, wrap up our morning session, right, and eat lunch, right? Let's agree that we're gonna meet here at 1 p.m. sharp, 13:00. Sophie, on my right, on your left, is gonna guide you towards a delicious meal. See you in a bit. Thank you. Hey, welcome back. I hope you all had a wonderful lunch. Did you enjoy the shrimps? Yeah, shrimps are good. And yeah. All right. Just to remind you, refresh you about our agenda, we're going to have a couple of speakers steal some real examples from how TiDB is being used in real companies, some insights how we develop our product. We're going to have 2 coffee breaks, still have them. We're going to have a happy hour at the very end of our event, where you will have an opportunity to talk to everyone you want it, ask questions, have some nice time with us in a more relaxed, informal situation atmosphere. Okay? All right. This being said, and hopefully everyone who wanted to come back did that already, I would like to invite you to explore another case. As I mentioned, this is one of the most technologically advanced banks in Europe, right? And they are currently making a new leap, a new shift after migrating to AWS. They are migrating their whole database systems, and they are migrating it, obviously, to TiDB. By the way, who of you know what TI stands in TiDB? You work for this company. Don't raise your hand. All right. What is it? Titanium, exactly. Because we believe that titanium is one of the best materials in the world, right? It's light, it's very durable, and it's very reliable. Those are the qualities that we value the most in our products, and that's why we would like to associate ourselves with this wonderful material. Anyways, back to the topic. Today, I invite you to go through the journey of implementing TiDB in one of the most restricted, right? We all know that banks are famous for not allowing a lot of freedom when it comes to choosing systems and software and everything. And what we were talking with Tarmo about 20 minutes ago, he has this kind of a key on his chest, and I was asking, what's that? And he said, you know what, even if I go to a toilet, I need to use this key because everything is secure in the bank, right? So this is the level of pressure that people are facing when they are choosing a new software. But yeah, I will let Tarmo speak for himself. Tarmo, please, welcome on stage. And this is for you.
Okay, let's start. I will not talk much about the bank, but I will talk about my personal experience. This is really important. And I want to show you that adopting TiDB in your organization might be easier than you expect. So I have done it twice. So this is one slide about me. So I have been in IT more than 30 years. By the way, I'm 25 years old. And I'm passionate about solving complex problems. I'm an open source enthusiast, because open source helps to stop reinventing wheel again and again. And instead of that, it helps to improve the wheel. And I'm an optimistic realist. I try to have not unrealistic expectations about any technology. And I was 8.5 years database team lead at Bolt. And currently, I work for LHV Bank, Estonian LHV Bank. And I'm an infrastructure architect at LHV Bank. And we compete with Swedish banks. They have more people, we have smarter people. So it's so good to be in Sweden. Okay, usually I'm a little bit sleepy after lunch. I don't know how about you guys. But let's do short warm-up. So how would you describe TiDB in 3 sentences? I know that you are already experts on that field. So what are the 3 main properties that come into your mind?
Reliable.
More?
Durable.
Okay. How would I describe it if someone asks? The 3 properties. It's slow, it's expensive, and it lacks or it misses some features.
Technical break.
No. Please don't leave the session yet, because I'm going to demystify this slide. But this slide is 100% true. Same time, it's a big lie. Is it true or lie for you? Depends actually on you and how you're going to use the TiDB. So the first claim. It's slow. Yes, it's slow if you compare it to the MySQL, and if you compare it the single thread performance. There's no point to compare the MySQL and TiDB one-to-one or like apples to apples, because TiDB is a different kind of database. It is a distributed database. In case of MySQL, if the query comes in, let's say it's a short query, exact point lookup, then the MySQL gets the query, executes it in the same machine. The data files are memory mapped. It's just a matter of, it's just a question of few pointer operation. MySQL gets the data and sends back. It cannot be faster anymore. But in case of TiDB is a distributed system. You had to count all the network latencies and so on. But the situation is pretty opposite. When you start to read more data, you send queries that read a lot of data. TiDB can execute those queries parallel because your data is spread across the storage cluster. TiDB reads the data in parallel, and all your slow queries are actually becoming faster. And that was about a single thread, but TiDB can process queries in parallel. It can do massive parallel processing of data, and TiDB can outperform MySQL easily. So, yeah, okay, the second claim, it's expensive. Yes, it is expensive if you self-host it for just for one small database. Let's say you have a WordPress site and you create a TiDB cluster, then of course it's expensive. It requires many machines, a lot of CPU cores, RAM, but things are going to change quickly if you start to store a lot of data, because TiKB is based on RocksDB. RocksDB has really good compression, and you can save a lot of data on the storage level. And yeah. And the last claim, very often developers come to me and ask, where are the triggers, for example? I don't like triggers. I consider triggers as a part of the application logic, and that's a good thing that TiDB doesn't have triggers and some other features. So that kind of protects TiDB. Developers cannot put the application logic into the database. It's pretty obvious that you don't store the data on the data application server. It should be otherwise too, that you don't put application logic inside the database. Okay. Backstory. Okay. In 2014, I joined small startup. It was really, really small startup. Name was Taxify, but the company got renamed Bolt. And my responsibility was to keep all the Bolt system up and running and performing 24/7. That was quite easy job at the beginning, but and we had only one small server, both for the application and database. And can you imagine, Bolt now has 200 million plus customers, but when we started, we had just one single server. And very soon we moved out to the database to another server. Then we had two servers for some times. And MySQL seemed like a right decision because it performed well, developers know it, and life was pretty good with it at the beginning. But soon companies started to grow, and it started to grow faster and faster and even faster. And guess what? Where all the data in the database. So databases experienced the greatest impact from this growth. And managing this database infrastructure became increasingly difficult and more difficult. So around 2017, I actively started to look for alternatives to MySQL, alternative solutions, because it was clear for me that we just simply cannot continue this way. So MySQL it's a great database. I really love it. I like it. It's mature. It's feature-rich. It's highly reliable. But things change. Start to change. Things that I don't like about MySQL. So it has really inefficient data storage. It wastes a lot of space. InnoDB has a bad space read and write amplification. InnoDB burns many IOPSes. And usually you don't notice it before you have a lot of data. And then you start to ask all kinds of questions about the efficiency of the data storage layer. Then the second thing, or maybe even the first thing, you notice that the replication is can't keep up. So you have let's say you have one big master server, a primary. There's many queries or transactions running in parallel, and then MySQL just takes and serializes all those transactions into one bin log, binary log, into one stream, sends it on the other side, and the other side, I mean the receiving side, the secondary has problems applying those changes in parallel. So, and there's more. One main thing that I don't like is that you can't scale MySQL horizontally. So you can add secondaries to speed up reads, scale the reads, but if you have lagging secondaries, then it's not the best thing to do. And you can, for example, you can scale reads by some simple caching layer usually. And if you build a cluster, MySQL cluster that needs to be up and running 24/7, performing, and you don't have any maintenance windows, then you have to do all the schema changes, all the configuration changes, everything on a working cluster, and that becomes super difficult and complicated. So, and this all leads to really high database infrastructure cost. And also, this is a huge business risk because if let's say you have backups that running half a day, what about the restores? If something happens and you need to restore your MySQL and your service and your business is down, then this is really bad. So MySQL, if you put a lot of data into MySQL, then this is a business risk. And TiDB very effectively solves all these challenges. Okay, this presentation is not about the MySQL. This was just background information. So the first impressions. Since I was actively looking for alternative solutions, in 2018, I attended Percona Live Frankfurt, and I met two Asian guys. They were really passionate about their new database they're building, and surprise, that database was TiDB. And TiDB, I looked at the architecture, and it looked exactly something that I was searching for. And what I really liked, that it had a separate compute and storage layer. Both layers were horizontally scalable independently. And I really liked how the replication was built. TiDB uses it chunks the data into smaller pieces and builds the raft groups from those pieces and uses raft logs to replicate the data. And this guarantees much better data consistency and also performance. And also, I like that TiDB stored data in RocksDB. So TiKV uses RocksDB, and RocksDB is based on LSMs, and LSMs are really effective on compacting the data and storing it in a very compact manner. And also, LSMs are like flash-friendly and don't burn out your disks. And also, I was impressed when I saw that all the components have built-in Prometheus exporters, and that cluster comes with Prometheus and all the dashboards ready. So the monitoring was included. I remember when before the PMM came out, we had Polt. We managed our own exporters for MySQL and created our own dashboards, and this was really something that we spent a lot of time. So, and then there was something else, HTAP. This was like something I asked like 3 times, HTAP, what does it mean? So, and when I saw the diagram, I was really impressed when I saw that, and I liked the idea that let's store the data universally in the storage cluster, And we can have then different, let's say, interfaces that use the same data. For example, we have the SQL interface. You send all your OLTP queries to the SQL interface, and then you have the, for example, TiDB Spark interface. So you can use that for complex online analytical queries. And looked super promising. And there was more. I even don't remember all the details. And then I went back to the office and introduced to my first two colleagues. They were very skeptical, like always. And then I started to test TiDB. And overall, it delivered everything it promised. I got it up and running, but I found some shortcomings. So I didn't like the setup. It was Ansible-based back then. Maybe the problem was my workstation, maybe the Python version, Ansible version. I spent quite a lot of time, got it up and running. Then documentation was incomplete. I remember that I had to read some scripts and some README files, and I had to use Google Translate to translate those files to English. And the platform felt still somewhat not production ready. So, and the main showstopper for us was that TiDB that time supported only the binary evaluation, and that was the real showstopper. So I was extremely disappointed. I had high hopes for the TiDB, but we were unable to use it even for less critical applications. So yeah, I was extremely disappointed. So we had to do something about our ever-growing databases. The growth was continuous, it was fast, and I was under great stress because of it. I knew a problem was growing, but we didn't have a clear path forward. So our options, first option, build sharding into the applications. I asked this actually since from the day one. I asked from the CTO and developers, and hey, please come up with some sharding, but nobody had time for that. We had to keep the business running and growing. And by that time, it was too costly, and we didn't have time to rewrite all the applications. So this option was out of question. So next option that came into my mind, since we had proxy SQL running already, and I developed some custom logic for proxy SQL. I knew the little proxy SQL source code, and I came to the idea that, okay, I built for us some kind of simple sharding, custom sharding logic, and that just chooses maybe the cluster or database based on the, I don't know, CTID or some other value. It sounded like a great idea, but then I spent like half an hour, maybe an hour. I started to count all the problems that I need to solve. So if I build sharding, there must be a resharding process. How do we handle the auto increments and cluster-wide sequences and so on, and at least continuous, and also that was out of option. Then MyRux. Who knows what is MyRux? MyRux is MySQL database storage engine based on RuxDB, so it uses LSMs to store data efficiently, the same way as TiDB. But why I ruled out this option was that we still can't have horizontal scaling. Even if we have better compression, we just win some time, but this is not a solution. And then Vitess. Who uses Vitess? Any Vitess users here? No, okay. So Vitess has, it's a middleware. It's based on the MySQL. It's a middleware. It sits between your applications and MySQL, and allows to scale horizontally. So, but yeah, it looks great on the paper. YouTube uses it. It's like their main selling point. At least it was back then their main selling point. And we had both discussed that it is based on MySQL. We know MySQL very well. We use it for everything. So let's migrate to Vitess. I was a little bit against it because I didn't like it because of the inefficient sharding, and there were more problems. So Vitess was us wrong path. So what was wrong with the Vitess? So first of all, maybe this is a small thing, but it was not easy to integrate it into our existing MySQL infrastructure. For example, the user management, I didn't like it at all. If you have in your company, if you have, let's say, some kind of user management system, or you use a HashiCorp or Vault database engine, you cannot use it for the Vitess. Vitess requires literally you need to rewrite your applications. So this is you can't avoid it if you use Vitess. And it introduces additional complexity to your applications, developers, and this is actually the worst thing, that developers must start to think about how your data is stored in the cluster. They need to understand the sharding concepts. They need to understand what is vSchema, how the v-indexes work, and so on. And I think if there's a technology that complicates the life of developers and they need to think about the databases, then this has a negative effect to your business, because developers, they really need to focus on developing the business logic, not think about database sharding. And it's still MySQL. The storage layer is very inefficient. And yeah, you can scale out horizontally, but you spend a lot of money on an infrastructure. And then I started to think about the first migration. It took 6 months, hard work, to rewrite the application. Actually created a new application. That was an easier approach. And then I started to think that we have 100 or more microservices. So if it took half a year to migrate one service, educate the developers, so it takes another 50 years to migrate all the services, even if we can speed up the whole process, because just repeating some of the migration parts, then still it's going to take years. But we were running out of time. So, and I want to say that TiDB again addresses all those problems. So, and TiDB revisited. So, since we were running out of options, I was under huge stress, couldn't sleep or eat, so I got the gray hair from that. Then I decided to have to look at TiDB again, and I was super shocked. I was honestly shocked in a good way. The TiDB I saw in 2021 felt like a completely different product. I remember asking myself that how is it possible that TiDB is so much better? So for some database technologies, it takes the whole decade to make this kind of progress. And I was really, really shocked when I started to read and learn about TiDB again. And I was shocked, much like the AI industry when the DeepSeek model first appeared. I asked, how come? So, and what I really liked about the new TiDB was that Ansible was gone. It was replaced by the TiUp. TiUp is a component and package manager for TiDB. Documentation that was incomplete when I looked last time was really, really good. I enjoyed reading. I remember that I read all the pages, at least twice. And I saw also major improvement in TiDB tools and tooling around the TiDB. The TiDB Lightning, I liked the TiDB Lightning, the DM was better, and And finally, the most important thing, TiDB supported collation that we were really missing. Somewhere around version 4 point something, TiDB introduced a new collation framework. And I remember when I tested it needed to be enabled during the cluster initializing time. And also, TiFlash was new. It was missing before. And I was super excited about TiFlash because I thought maybe we can replace our super expensive AWS Aurora, sorry, Redshift, and use it for analytical. And everything looked better. It performed better. It was easier to set up. The monitoring was better, and the documentation was super good. So then what I did, I took short vacation. I took 3 days off from work, went to vacation, spent some time on evaluating TiDB. That was the best vacation ever. I don't know about my wife. She's still my wife. And what I tested and what I evaluated. So first I started with the cluster management because TiUp was new. I tried to deploy the cluster, scale in, scale out, upgrade the cluster, just replace the cluster nodes. Then next thing was that was really important for us. I tested how the new collations are working. Then I decided to do something real. I exported from one of our systems. I exported a lot of data and used Lightning to import it. Imported a lot of data. Then I set up the DM because I wanted also replicate all the data and see how the replication works. Replication worked great. I was very happy. Then I tested how to get data out from TiDB. So it's pretty logical that if you put it in some point in future, you may want to get it out. And when I got the data out, I imported it in the MySQL and tested DICDC and replicated data from TiDB to MySQL, and it worked like charm. And then I tested the backup and restore procedures using the BR, and did all kind of data validation testing, and I couldn't find anything. So, and then I collected production query samples from the production environment, and these are the results. So I was again very amazed and happy and shocked in a good sense, because everything worked, and everything worked even better than I expected. The cluster management with TiUp was really easy and convenient. The documentation matched reality, so it's very often case then when you start to use new software and you copy and paste those hello world examples and nothing happens, but that was not the case for TiDB. So every example worked as expected, and I repeated all the tests and several times, and every time worked. And I liked the performance, because I remember the first test I did, I used 3 terabytes of data. I used Lightning. I chose the really big instance from AWS with 96 cores or something. And I was amazed that but the TiDB Lightning was able to utilize very efficiently all the cores, CPU, memory, and it was really, really fast. So it created all the RocksDB SSD files and uploaded to the TKV nodes, and that process was really, really smooth and fast. So I expected that it runs like half day or day, but no, that was maybe less than an hour. And that was the most important thing. Remember with this, when I collected query samples from the production systems and tried to run on Vitess, almost 100% queries failed. But for TiDB, 100% queries executed and run successfully. So this is really strange, since Vitess is based on the MySQL. How come? And TiDB is a different kind of database, and it's a distributed database, and all queries run. And yeah, overall, I was very impressed with TiDB's quality, because everything was really high quality. I didn't encounter any major issues. I liked the documentation. It didn't corrupt any data. It performed well. And after all of that, I was absolutely convinced that PingCap was super serious about building and improving TiDB. And the second thing was that I was convinced that TiDB was the right strategic direction to bolt. And then I went back to office. My next mission was to replace MySQL and Vitess. And when I went back to office, I introduced TiDB to my colleagues again. They were super skeptical. I introduced some cool features like the flashbacks and so on. And then one colleague said that that's not a database, that's a Chinese magic. But a few weeks later, TiDB was up and running in our test environment. And I had planned to put it into production. But then I had a meeting with the director of engineering. He was also super skeptical about TiDB. He said that we spent so much time and effort on migrating to Vitess, and let's not migrate to TiDB. And I said that Vitess, it looks nice on the paper. The situation is like the same. You walk on a street. You're walking on a street. You meet a nice, beautiful girl, you'll marry her, and later realize that she's not the one. And I said that Vitess, it's like a bad marriage. So, and asked, what are you going to do? He said, I'm going to suffer. I said, you're strange man. And this is how we ended the Vitess story. And then I prepared for the first migration. This is the true story about the first migration at Bolt. So, this upstream cluster was the cluster that was serving the production workload. Proxy SQL was there already before I created TiDB cluster. I exported data from the upstream cluster, imported the downstream cluster, set up the replication, and we sent some read-only queries to the TiDB. And for recovery purposes, I created one MySQL cluster, put behind TiDB, set up TiCDC, and set up the replication. So, and I kept this setup like a few weeks, monitored closely the replication, the backups, everything performed well. I don't see any issues. And same time, we had meetings. And the main topic was always, are we brave enough to switch production to TiDB? And we had meetings and meetings and meetings. And on one Friday, I got enough. I just let to know one senior engineer that, hey, I'm going to switch your database to TiDB. And that was really stressful moment. I prepared well for that. I had multiple monitors on my desk. I opened all monitoring tools. And I prepared some scripts. So, and I set the first MySQL read-only and removed from the proxy SQL. The scripts also verified that all the data is already in TiDB. Since there was no slave lag, the cutover process was really short, 2 seconds. And yeah, you know what happened after that? Nothing happened. Application kept running. I was expecting much worse. Only errors I saw were from the applications during that read-only period. But after that, everything kept running. I afraid the most that I afraid the latency rise, but that was the average latency before the cutover was 1 millisecond, and after that it was 6 or something like that. I expected much higher latency rise, and the TiDB cluster was set up over the 3 different availability zones. That also caused the latency rise a little bit, but that was acceptable. So, and then after a week or so, I removed that recovery cluster and also deleted the old upstream cluster because we realized that we don't need it. We don't need those clusters. But after the cutover next Monday, we had again meeting. And the topic was the same. Are we brave enough to migrate to TiDB? And I said that we are already in TiDB. The production runs from TiDB. And I almost got fired. Maybe 2 or 3 times on this week. But same time, everybody were happy. Everybody's eyes were shining. Okay, enough for the bolt. So after 8.5 years, I got tired. I needed a break. And in 2023, December, I joined LHV Bank. Yeah, this is the correct name, the bank. It's Estonian LHV Bank. And when I joined, my work was not anyhow related to the databases. So my main responsibility area was to keep the Kubernetes infrastructure up and running, and also one of my tasks was to modernize the aging infrastructure. And I don't know if you have noticed or not that there's always somewhere in your infrastructure there are databases. So if you start to modernize, you sooner or later end up there. And in 2024, we started to discuss the future, what to do about our aging databases. We have all kinds of databases. Microsoft SQL, Oracle, Postgre, just you name it. And it was very easy to agree, and everybody agreed that let's use open source databases. And since I'm an open source enthusiast, I believe that it is I think it's important not to use closed source software for your most critical parts in your infrastructure. And then when we try to agree what database we are going to use, what open source database, the list is actually really, really long. I had TiDB in my mind on that. And we couldn't agree, but I suggested that let's agree what wire protocol we're going to use. Is the Postgre MySQL? And I favored MySQL protocol. I managed to convince my colleagues that if we use the MySQL protocol, then we have more databases to choose that use MySQL protocol and more migration path. And yeah. And then in 2025, I got a call from my one colleague, and he asked what I think about migrating the bank's history, 15 years of history, into the TiDB, and asked, can it be done? So I said, okay. Then he asked that can TiDB handle so much data? So I said, don't worry, the bank doesn't have that much data. That's true. TiDB can handle way more. And then he asked what is the realistic limit of TiDB? How much can we store data there? And I said that the limit is credit cards, so limit. And luckily, that credit card was issued by our own bank. So yeah. And then it was silent, maybe 30 seconds, and then he said, yes, let's do it. And this call started interesting project in our bank, migration to TiDB. But bank, it's not a startup where you can just start a random database and put the data into it. So instead of starting with migration, we started with paperwork. Same time, engineers started to work on the plan how to get data out from those different databases that are not MySQL databases. And this is the final plan that we came up. So the data was exported from 3 different databases. Then it was merged, transformed and merged. And the output of AWS Glue were the Parquet files. And then I used TiDB Lightning to import those Parquet files from S3. That was the easiest part. And then since the data was migrated out from 3 different databases that the DM data migration doesn't support, then the incremental data was replicated on the application level. So we have really good motivated engineers. I'm really proud of them that they managed to do this. And then we started to send some traffic to newly created service that used TiDB. You know what happened? Nothing happened. Everything kept running. And then maybe a few months later, the whole traffic was, 100% of traffic was switched to the new service. And what happened then, I don't know, because I missed that moment. So I want to give some practical advice for you, adopting TiDB in your organization. First of it, you need to learn it. And the easiest way to learn is to start by experimenting. The easiest way is to use TiDB Cloud. This is the fastest way for you. Just a few clicks and you have TiDB up and running. But if you want to go deeper, you want to self-host it, you want to run it in your local environment, use TiUp Playground that starts clustering in your local environment. Very important, please read the documentation and make sure you understand what you're reading. Pay special attention on the architecture documentation and read at least those pages, the architecture overview, storage, computing, scheduling, and what is the TSO. Because if you understand those concepts, then you almost immediately understand what is the TiDB and how it behaves and what properties it has. And one more very important thing, so please don't get stuck into the MySQL and MySQL features. Explore the TiDB's unique features. Why you need to learn it? You need to learn it because if you want to adopt in your organization, then you have to introduce it to managers and colleagues. They'll definitely start to ask all kinds of questions, even very technical questions sometimes. If you have all the answers, then it's okay. If you don't, it's bad for you. Demonstrate the capabilities, what TiDB can do, so how the organization can benefit from it. Organization maybe can save a lot of on infrastructure costs. And this is very important. If you help to adopt the TiDB, then you're probably the first person who needs to support your teams and colleagues. And invest on training and knowledge sharing. I really wish I have more time for that. And be patient. So you have to maybe repeat all the steps several times. And that's all. Thank you.
Thank you, Tarmo. Beautiful presentation.
Thank you.
So just to make clear, the main thing that we need to get from your presentation is the best way to spend your vacation is by learning TiDB, right?
Yes.
Hands down.
No,
Yeah. You know what you need to do this summer, right?
Yeah, no, you need only 3 days, not the whole summer.
Yeah,
because if you read those
okay.
pages I showed you, then you don't need to spend any more time. You understand it immediately.
No. Yeah. That's how easy it is.
Okay.
And yeah, thank you, Tarmo. Talking about, well, one thing, right? When you saw me hurrying up to the stage when I saw this slide, like TiDB is slow and everything, that was not acting. Because we don't verify slides from our speakers. What we usually do, can you talk about TiDB and can you talk, and they would ask us, what do we need to talk about your journey? That's what we ask, your experience, but we never moderate. So at some point, I was really thinking that Tarmo is going to say something bad, which is okay, that is fine, but like you could have told me, right? So you got me there, Tarmo. Thank you. Anyways, moving to the topic of how to quickly learn TiDB. Maybe some of you were sitting here and thinking to yourself, okay, this is all good stories, right? But when we're going to more practical things, how applicable all the things that's being said, being announced from the stage are to my current situation, right? And Daniel is one of the main person who helps our customers to answer this question, right? He heard this question, is my system compatible with the current setup with TiDB? More times that he can count, I think. Daniel is a technical solution engineer, and today he's going to answer a question how easy it is to migrate to TiDB. Daniel, please.
Hello. So today I'm going to talk to you about migrating to TiDB. So a lot of the talks before have been talking about the whole journey from like why you want TiDB to the eventual solution, all the great features about TiDB. I will be focusing a little bit more on the actual migration. You have your old database, you have your new database, how to get there. So I will start with a quick introduction, then we go over some basics about the migration, and then I will go over some things to watch out for that you might want to pay some attention to while you're doing your migration. So I'm Daniel van Eden. I'm a technical support engineer, so I've been working with companies like Bolt and quite a few others to get them to actually use our product. I've been helping with some training, I've been helping with documentation and many other things. Besides the support part, I've also been working on actually contributing to TiDB itself, including all the tools like TieUp and a few other things. But I've also been working with MySQL. Before I joined PingCap, I've been working at Booking.com, where we run like a really large MySQL infrastructure to support all the hotel reservations and things. So I know a lot of things about MySQL. One of the other things I've been doing is maintaining the Go MySQL library. This is one of the libraries that's being used by DM, data migration, to actually look at the changes from MySQL and being able to use that information during the migration. Wireshark is also another open source project that I've been involved in. There, like, we decode the MySQL wire protocol, so I know quite a lot of things about the wire protocol itself. I've been helping to improve the features in TiDB for better compatibility with the wire protocol. And I'm also maintaining the DBD MySQL driver in Perl. And as you can see there, I have other ideas about vacation than Tarmo. Although I might have been guilty by working on TiDB in weekends and vacations, but I like to go into the mountains when it's possible. So let's go over the migration basics first. So the source, usually MySQL, because that's our main focus, because we are MySQL compatible both with the wire protocol and the syntax. And the target is, of course, TiDB. And the tools we have for this is data migration. You might have seen it being mentioned multiple times before. And the platform that I will be using for this today is TiDB Cloud. So we start with a quite simple setup. You have an application, you have your MySQL database, they talk to each other. What's the next step? Well, the first step is to actually create an instance on TiDB Cloud. And then you have the database, but then there's no data in there just yet. So then you need to use data migration with TiDB Cloud to actually get the data to the TiDB database. And when that's all working, you can actually like maybe have a copy of your application that does some read-only work on your new database to make sure that everything is working as expected. And if that's all fine, then you can just switch over to your new database. Maybe keep the MySQL database as a backup for a bit. You don't need to use the data migration anymore. And then eventually you get rid of the old database, and your application is fully working on TiDB. And from that moment on, you can start to use all the new features that TiDB has that MySQL is lacking, like factor search and these kind of things, and branching and whatnot. I was planning to do a short demo of this, but I decided that demo might not be the best thing to do with the amount of time that we have. So what I did instead was to use a few screenshots. So for the demo, I had a simple to-do list application to make sure that we have some data that we can actually migrate. It was running in MySQL 8.4, and now we want to migrate to TiDB Cloud. So this is what the application looks like. It was fully vibe coded to just have something. The to-do list has to-do items. It has categories, and then like items get assigned to categories, etc. So it's fairly simple, but it's a useful application. So the very first thing we need to do is to actually create a TiDB Cloud instance. As you can see on screen, there are different tiers. So there's Starter, Essential, Premium, and Dedicated. Here we will be using Essential. After creating the database, you also need to actually set up the root database user. And once you have done that, then this is the next step, is to actually create the migration job. So it might be using like a TLS or other things, might be using a private endpoint if needed. And here you basically specify all the things that you need, like the username of your source, username for your target, all those kind of things. And once you're ready, you click on Validate. And then the next step is to actually select what you want to migrate. So the objects here is just all the tables for this specific application. And the other thing you select here is in the migration process, we have selected full and incremental. So full and incremental means that we will first do a full copy of the data, and then we will keep streaming all the changes from the source database to the target database. So it keeps being updated constantly. And then we create a migration job. So the pre-check has finished. It gives a warning about foreign keys. So the application did have foreign keys, which are not fully supported during migration. Afterwards, they are supported. But because of how MySQL works with foreign keys, there are some iffy bits there. So that's one of the things you need to keep a bit attention to, like how that works. So for now, we can ignore this warning. It's good to have seen that this is one of the areas where we need to look at later. And then it gives us a summary of the migration job with all the information about the source, the target, and what to migrate. And then we start the migration. So you can see that the migration was running, and of course this is a tiny application, so it's done almost instantly. So once this whole migration is done, we can actually start to use this database, but because of the incremental migration keeps running, you should not be making any changes to the target database, but you can already do like read-only queries, see if all the data looks correct, make sure that all the data migrated, that you maybe have selected all the tables that you needed. Maybe you forgot one, or maybe there's something that's specific to MySQL that is not supported in TiDB. So this is a good moment to actually check things, and then eventually you can stop the migration job if you have switched over, for example, or if you want to maybe do it again. So the next step is like migration complexity. So this was a to-do application, fairly simple. The only complexity was the foreign keys, which we basically just ignored. And because there's no changes being made during this whole migration, it's really easy thing to do. But in real life, things are less simple. So what do we actually do during the migration? Well, the initial full migration means that we need to do a logical export, because MySQL uses the InnoDB file format, so we cannot use a physical copy because we don't know how the InnoDB file format works. So we need to get a logical copy, and we need to do this in a way that's actually fast. Because if you do this like one table at a time, one row at a time, it will take ages. So we need to get a very fast logical export. Then also for the schema, we need to figure out which tables to copy. And then the table content is easier, but we also need to do the right kind of chunking during the copy. And then for the ongoing migration, we need to follow the MySQL binary logs. So we will tail the binary logs like a MySQL replica would do as well. So the row-based changes get applied constantly. And this is what allows you to do the read-only testing with more or less up-to-date data. So for the source database, MySQL 5.7 and 8.0 are fully supported. 8.4 is not fully supported yet, but that's one of the things we are working on. There were a few small changes being made in 8.4, so that's why there are some updates needed there. This also includes things like RDS and Aurora. There's a full list of compatibility items on our documentation. Like what Tarmo said is like, make sure you read the documentation because there's a lot of very useful information in there. If you're migrating from MariaDB, there might be MariaDB specific things like system version tables and other things that we do not support. So that's one of the things to look out for. We also have good documentation on this. If you're using an ORM, things might also be easier because some of the ORMs actually support TiDB, and you can just like change your database flavor to TiDB, or keep it on MySQL if there's no TiDB specific flavor for your ORM, and that might make migration a lot easier sometimes because then it might generate SQL statements that are actually compatible with TiDB and might not use something that's maybe not as compatible. This also works for migrations that are not from MySQL or MariaDB, but from like Oracle or SQL Server. Like if you're using an ORM, you might be able to just create MySQL style statements instead of the Oracle and DB2 ones. So usually you will be using data migration, but you don't have to. There might be cases where maybe like there's a network issue where you're not allowed to actually have the network opened up for to TiDB Cloud, for example. And then you can use dumpling, which is our data export tool, to actually make a dump in to files and put that on S3, and then you can import it again on TiDB Cloud. So data migration is not the only way to do this, but the great thing about data migration is that this does the incremental loading and keeps your data up to date. So for TiDB Cloud Starter, you might also want to do like a dump and restore, because there we don't have the data migration supported. But you can run an actual data migration yourself on your own machines if you want, because it's an open source utility. So that does work, and it does only need, it does work with TiDB Cloud. One of the things that you might notice afterwards is changes in how auto increments work. By default, auto increments in TiDB are given out per machine. So if you have, like, say, 3 machines, each machine gets a whole batch of auto increments, and then depending on which machine you're landing on, that's the machine that's giving out the auto increments. So the ordering of that might be different. Should not be a problem in most cases, but if it is, because you might want to, like, order things, you might want to look at this and make sure that this is working as expected. We have multiple options for fixing this. So one of the options is to basically have a cluster-wide auto increment service, so that the ordering does work in the same way as MySQL. So you don't have to change your application, you just have to change the configuration. The performance is slightly lower, but it's still quite good. And the other one is to actually have another column with like a microsecond timestamp, and then use that for ordering the tables. So this is like an example of what you might be seeing. So on 2 different servers, you get like wildly different numbers, and then the ordering might be off. So that's something that's seen quite a lot. Hotspots can be an issue, but a lot of people are looking at hotspots and like, okay, we have to fix those possible hotspots on TiDB. What I've seen is that it's often not really an issue, because you have so many tables, so many indexes, so many things going on at once, that this one table that might be having a hotspot issue is usually not really that much of an issue. It's not causing a big imbalance in your database. So what are hotspots exactly? So if you use an auto increment, of course, all the numbers are like in the same range, and numbers in the same range are written to the same data region, the chunk of the table. And this is on a single server. It has copies on other servers, but all the writes go to the same server, although it's usually splitting this into like multiple data regions quick enough to actually, for this to not be as much of an issue. This can not only occur with auto increments, this can also happen with UUIDs. And the thing is that with TiDB and with MySQL, what you need to do for UUIDs is the complete opposite. So for MySQL, you want UUIDs that order in the same way to make sure that you're not splitting pages constantly. For TiDB, you want randomness. Normal UUIDs don't work very well on MySQL, but they do work really well on TiDB. I'll just skip over this one. Yeah, foreign keys, I already mentioned this. This needs to be handled with a bit of carefulness. It really depends also on like what MySQL version you're using, because newer MySQL versions will actually send more information in the binary log, and then it might work as expected, but it might not for all the versions. There are some features that we do not support. Most known is the stored procedures, stored functions, these kind of things. So if your database application is using any of these, well, you should make sure that you have some other option. For many of the stored procedure things, actually using a microservice might be a better option anyways. And with change data capture and events in Kafka, you can often emulate things like triggers. I'll just some best practices to end my presentation. Read the documentation. Make sure you look for all the supported versions, look for the required permissions, required versions, and whatnot. Keep your application database in the same region. Test before you do anything in production, and make sure you involve us from the start. Like tell us what your plans are, tell us what your needs are, because we might have special information like watch out for like this functionality, or like we're working on this feature that might be useful for you. So make sure to involve us as well. Thank you.
Thank you, Daniel. Yeah. So this is like a great example of people that are trying to help our customers implement TiDB at place. So expect very friendly attitude. I would like to remind you that today everyone who wears this kind of polos is at your disposal. So whenever you have questions about our product, feel free to approach to any of us. Yeah, we're all happy here to answer your questions, crack a couple of jokes, help you to the bathroom, whatever, right? Treat us as you want. Now, our next session will be a live demo, which is exciting and rare thing nowadays. But before that, let's take a 10-minute break, have some coffee, all right? I see what's the problem here. So the local buns are too tasty, and we have too many of those. So people just want to grab as many as they can. I personally had 2 of those. They're delicious. I can understand this. Anyways, we still have a lot of sessions to cover, right? A lot of topics to discuss. So we will move forward. And I'm especially excited about the next session, which as I mentioned before, is going to be a live demo. And as we all know, live demos are a tricky part, right? For example, Apple doesn't do live sessions, live presentations anymore, right? But we are better than Apple, of course. We are brave. We can do this. We believe in ourselves. And it's always exciting to see if something goes wrong, right? So Mohammed is a software architect at Scania. And today, he is going to build a real multi-agent system live using Google's Agent Development Kit and MCP servers on Python. Is it correct? Yeah. Mohammed, please, welcome on stage.
Thank you.
All the best.
Thank you. Okay, everyone. I saw a lot of you when I came here, and now there's few of you. So let's... it's the buns. Everybody wants to sleep now. All right. So 20 minutes, and I'll show you how you go from 0 to an agentic orchestra. And when I say agentic orchestra, I mean you have different kind of agents that work with different requirements and different workflows as well. But before we start, I want you to quickly take out your phone and scan this. This allows you to access all the resources I'm going to be mentioning in this talk, and also give feedback directly to me if anything needs to be improved, or if you love the talk absolutely. So all of that is possible. So I'm just going to give you some seconds, and then we will move forward from here. Awesome, and I'll show this later as well, so you will have a chance then. And I can already see some reactions coming in as well. So very nice. So who here likes AI? Show of hands. I'm looking at especially those who are not raising their hands. Okay. And who uses AI just for coding, nothing else? Okay, 1 person, good. So do you want to know what I use AI for, especially when I'm not really coding and I want to take my mind off of it? I do something like this. And I don't want to fool you, because this is not AI. This is years of practice by myself. But this was not enough, so I was like, okay, I'm going to take this, and I wanted AI to generate a super realistic image from this, keeping the exact pose as much as possible. And this is what it generated. So maybe in a year or 2, you and me would be flying while coding. But this did not satisfy, of course, my curiosity, so I was like, okay, no. Take this, and take this guy as well, which is myself, and then generate something, and this is what I got. So now you've seen something that I am trying to hide my wife from. She should never see this. But then the next turn was this, and I have no clue what's happening right here. So yes, we got to be careful when using AI. But let's talk about agents. We have had agents for some time now, and the fun fact is that we are still struggling to understand how do we use them optimally. You would hear terms like prompt engineering, context engineering, harness engineering, and this will keep on changing until we have an optimal solution, so to say. The biggest problems with agents is that we try to make them do too many things at the same time. For example, plan a marketing campaign for my new application, research the trends, write messaging, draft the ad, copy, suggest visuals. You can see there are so many problems, and I'm pretty sure many of you would have tried to do the same thing, having a big prompt given to an agent to do something. And the question usually becomes, what could go wrong? And what goes wrong is that your agent becomes something like this. It tries to do 5 things at the same time, and it becomes really hard to track and trace what went right and what went wrong. For example, there could be some problems that I can already tell you. The model context overflows. This is something that happens, doesn't matter which agent we are using. We will reach the context length really soon. We also see that the model starts to hallucinate, and that is because the earlier instructions get lost. We also see that you can't test one step until you run all of it, because you give one prompt and then it has to do everything, and there's usually no way to go back. When it breaks, you don't have any idea why, so you probably just start a new session and hope for the best that it works this time. And then you cannot really swap out a single part if you're using one single big prompt. So what we try to do is essentially what we have been trying to do for the last 40 years as software developers. We try to decompose the problem. We go from making our agents to an orchestra instead of a soloist. In an orchestra, the violinist does not play the drums. The conductor does not really play any instruments at all. Everything or everyone has a specific task to do, and that is what I'm talking about. And I'm talking about this in the context of Google's Agent Development Kit, which I believe right now is one of the easiest way to get started with agents. So what is it, essentially? It powers Google's own agent space, or now they're renaming the agent platform to the Gemini Enterprise Agent Platform. It also was announced in 2025 at Google Cloud Next, and it's really easy to work with. It uses Python. You just install the package, write maybe 50 lines of code, and that's pretty much it. And it works really well because you get to see what your agents are doing visually, and I'm going to show you that in a bit as well. But before all of that, let's go through the basics. The Google ADK has 4 building blocks. The first one is the base agent. Everything in ADK is derived from a base agent. Now, there are different kind of agents. The first one is the reasoning agent, which is the LLM agent. So any agent that you're going to create that's going to use a model, that is going to be an LLM agent. Then you also have workflow agents. Workflow agents do not really do anything on their own. You create workflow agents to create workflows. For example, you could have a sequential workflow for agents. Do this first, then do this, and then do this. Or you could have a parallel workflow where multiple agents start together and then come back with the results of their own. And then you do something with that. We also have something called loop agent, and that is what you would use when you want to iteratively do something multiple times until there's a case for exiting the loop. And we are going to talk about that as well. So how do agents talk to each other in this case? We do have multiple mechanisms for this. We do have a shared agent state that all the agents on the same level use. We also have LLM-driven transfer as well. For example, the parent large language model can decide which child LLM to use. And then also, we can wrap the whole agent as a tool. So you might have heard this terminology of agent as a tool. So you can use your agent as a tool in other agents as well, which becomes really powerful when you're composing agents together. So now we're getting started with the really basics of it. The code that you see on the screen is all you need to create a simple agent, and that is pretty much it. You start with an agent.python file, you import the LLM agent from Google ADK agents, you can add a tool as well if you wanted, and then you create an instance of an LLM agent where you give it a name, the model, the description, the instruction, and also the tools. Now here I want to highlight one important thing. The name is, of course, just to identify the agent when you're looking at it, or when the ADK has to decide which agent to pick. The description is essentially for the ADK framework to understand what the agent does. It is not for the AI model to know what to do. It's for the ADK framework to see what this agent does, and that's how it identifies which one to pick. The instruction is essentially what takes, or what the model takes, to understand what it needs to do. So every model would have an instruction, and this is the prompt that we give to the model. So you can call it system instruction, for example. And then we have the tools that we can use. We have some built-in tools, for example, Google search, but you can also use your own custom tools as well. So I already explained this. I'm going to quickly move from it, but I want to also highlight the last one. This is really important. When you're working with a workflow of agents, an orchestra of agents, every agent, when it has to pass some information to the others, it emits an output key. or it emits data in a particular output key. So the others can read that. For example, if you had a researcher and a content creator agent, the first one would emit its research. And then the content creator can pick up that research and then continue from there. We're going to see that in just a bit. When it comes to tools, tools are basically just functions. How many of you have already worked with tools with agents? Okay, so a lot of you would be new to this. But tools simply are just functions. In Python, they would be really simple functions that would have a particular structure of how you create them. You have to have a comment that ADK reads and understands what parameters are there, what the function does. And then when you return the data, you basically return that as an object. So ADK understands, okay, this is what's going to be returned as well. The output key, I already mentioned that. So let's actually have a look at the first agent. So I'm going to exit from here. And let's go to our simple agent now. So if I go to the simple agent here, I'm going to ask it, what is the weather in Stockholm? And here you can see it does something. But before that, let's actually jump to the code. So I'm going to quickly go ahead and go to the single agent and the agent Python. So this is the code for this whole file. You'll see that a bunch of it is just comments, so you can ignore those. This is the function or a tool that this agent has. When we talk about tools and agents, you can imagine agent being a full computer, so to say, where the model is the CPU. It's going to be the brain of the agent, but the tools are the hands of the agent. Because imagine this, if I go to an agent and ask, where can I stay next week in Stockholm if I wanted to stay near the city center? Now, there could be listings from Airbnb that may not be already there in the data the agent was trained on. Every agent that we have has been trained on data from 2025 or before that. So if you ask it something, it only understands that it can answer from the data it was trained on. But when we give it tools for external data, it has the possibility to go and fetch information from here or here and then brings it back. A really simple example that I usually show in my workshops is the concept of getting the current time right now. If you ask Gemini or ChatGPT, what time is it right now? And if it doesn't have any tools, it would not give you the right answer at all. So the basic tool that usually is there is a simple Python function or a function that runs a simple code to get the current time. Similarly, we have this getWeather function, which essentially has some hard-coded information. For example, Stockholm has a sunny weather right now, 22 degrees centigrade. If I ask about London, then it's here. If I ask about something else that it doesn't know, it may not be able to answer. For example, if I ask what about Karachi, this is the city where I'm from. So here you can see it says I could not find any weather data for Karachi because it uses a particular tool. And you see that when I ask a question, it executes a certain tool. It executes the tool, it gets back the answer, and then it sort of humanizes it or makes it human readable, so to say. So this is a really simple example of how an agent works with some tools assigned to it. Now let's move forward. Now we're looking at a sequential agent, and a sequential agent, as the name says, it is supposed to have a sequence of agents working together, and each agent can emit an output that the other one can read. In our example, we are essentially having a coding agent. A coding agent would have first the writer agent writing the code, which is this peach/color. Then we have this brown reviewer agent. And then it reads the code that was emitted from before, and it then analyzes it. Does it really need to improve or something? And then it gives a review of it. And finally, we have a refactor agent that finally refactors it, and then the whole process ends. So how do we create this? Here's the example for the same thing. What we do here is that we import the LLM agent as before, but we also have something called the sequential agent. So first, we create these three agents side by side. So we have the first LLM agent, which is code writer. It has the model Gemini 3.5 Flash. It has its own instructions. And here is the important bit. Here is the generated code that it emits out. The code reviewer goes ahead and uses that information. It's really important to put this into the curly braces. So the ADK framework then picks that information. And similarly, when we have the code reviewer submitting its analysis, it emits it in the form of review comments. And finally, the code refactor goes there and then reviews that as well. So it has the information of the generated code and the review comments as well. And finally, it refactors it. At the bottom, this is where the sequential agent workflow comes in. Here, I'm combining all these three, the writer, the reviewer, and the refactorer. So all of them run in a sequence, and obviously the sequence in the array matter how you provide it. So let's have a quick look at this agent right now. So I'm going to go to the ADK web here, and I'm going to go to sequential pipeline, and here I can say write a function that checks if a number is prime. So you'll see the sequence executing, and what's really nice about ADK here is that you can also see, them right here as well visually, like what's happening. It first did the code writer, then the code reviewer, and then the code refactor as well. And you can follow it up with all the events as well. So I can see the agents right here. If I go up, this was the code writer, this is the code that it wrote, and here it says no major issues found. So the refactor then did not really do anything. Might have changed something with the comments, but not really a lot of changes here. Then we go to the next one. Yes. The next one is the parallel agent. And this means that these parallel agents that are supposed to be spawned together do not depend on the data at all. For example, a really good example that I use, or an agent that I use myself, is when I am looking for a topic that I want to create content about, for example, a LinkedIn post, an Instagram post, a Facebook post, then I essentially just have a researcher. The researcher researches and then emits out an information, and then three parallel agents start together. And they go ahead and create a LinkedIn post from it, the Instagram and Facebook, and these three are not dependent on each other, so they can work simultaneously. In this particular example, we are having a few researcher agents that are supposed to do a research, and then there's a synthesizer which will synthesize all of that research together and generate a final report. The example I'm using right now here is searching a renewable energy here, but you can obviously give it the possibility of asking the topic from the user. So we have three agents here, the renewable researcher, we have the EV researcher, and then the carbon researcher right here. And then we have the parallel agent combining these three. So these three are supposed to run at the same time. Then we have the synthesizer. Now at the end, this is the root workflow. So first, we have to have the research team working. So three parallel agents start together. After that, it goes to the synthesizer. So let's have a look at this example as well. So I'm going to go to the parallel research agents here, and I can say do the research, because it already has the instructions to do it. Now you'll see that these three agents that are right here, they start in parallel at the same time, and they also use the Google search tool right here. And this is a built-in tool. So you will see that the research that they're doing, what kind of search that they are doing, and what are their sources as well. And this is really important when you're actually building agents that will go to production. This ADK web locally allows you to test them, see what they're searching, what their outputs are, and actually investigate each single part of the process, and also the state where you can see the data that the models have as well. So we're not going to go into all the parts, but I think you'll be motivated enough today to look at this on your own. So here you can see that these were the three agents that went into parallel. And this is the renewable result, this is the EV result, and then this is the carbon result. So it doesn't matter which one finishes first. When all of them are done, then they go to the synthesizer, and then it takes the data from all of them and then generates a summary out of it. One of the things that you would have to look into when you're working with parallel agents is that you cannot have the same output key for all of them, because whichever finishes last is going to be the result in that case. So one of the common mistakes is to use the same key, like a result. Instead of that, every one has to have their own unique key, so the synthesizer can analyze those as well. Now finally, we have this loop agent, and this is really powerful when it comes to the harnesses that usually we see in Google Gemini, Cloud Code, Codex, because you'll see that it tries to plan when you ask it to plan something, especially around code, and it keeps doing that. It keeps checking files until it has a solid plan, and this is exactly something where loop agent could come in. But you would have to have two important things in the loop agent. One is how many maximum iterations it should do. Otherwise, it can go forever, and you'll obviously consume a lot of tokens. And the other one is when does it exit. And when it wants to exit the loop, what happens is that the loop agent emits a sort of signal here, which is escalate set to true. And when that happens, the parent agent stops the loop agent, and then it doesn't go beyond that. So here you see we have an example where we have a function called exit loop. There are a bunch of things happening there, but this is the most important part. Here you can see we are saying tool context.actions.escalate equals true. This is notifying the parent that we have to exit the loop. Now we have in this particular case another code writing, or not a code writing, but an article writing agent, where I could pass it a document or a topic, and I can ask it, okay, generate something for me. Then there is a critic agent, which is going to critique in terms of grammar, formatting, and things like that. And then this loop would go on, so it goes from writer to critic to writer to critic until the critic is happy. When that's happy, then the refinement loop essentially ends. So before we go to the pitfalls, let's actually try it. So what I'm going to do is, this time I'm going to deliberately give it something that it can write, but also make mistakes there. So for example, I can say write something about AI in 2026. Ooh, 2026. Make some mistakes in grammar and I would say formatting. And I can also qualify it by saying for the first time. So it doesn't keep doing it, because the first one goes to the root agent and then it goes to the critic. So here you can see we have the current documentation that was generated. And now you can see the critic agent here is giving the feedback. So the grammar and subject verb agreement is not correct here, pronoun usage, blah, blah, blah. Then the writer goes again. So this is the second iteration of the writer, and then it found more issues, and now it keeps going on until the critic is happy. So here you can see we have finally an exit loop where the critic is happy that it has done its job well. So this is a really good example of where you could use a loop agent. And here, again, the problem that you would have to avoid is that how do you ensure that the writer or the first agent does not get executed so that it sort of gets stuck into the same loop, because you're giving it some instruction, and it's really important. For example, for the first one, if the writer was supposed to use critique in this example, and the first iteration does not have a critique because the writer starts first, that will break the agent. So we make this critique an optional parameter. If you have a critique, then you do it or you work on it. Otherwise, you just write it on your own. So there would be things that you would see that can crash the loop agent, like not having max iterations, not having an exit loop, or variables or state like this that are mandatory instead of being optional. And finally, we are putting it all together. We now have an orchestra of agents right here. So here is the example that I talked about. So we have a research team, which is a parallel research team. I'm going to give it a topic. It needs to research the trends around that topic. It needs to research the audience around that topic, the competitor analysis as well. And finally, it's going to go towards an outliner. So it will outline the draft for me. Then it will create a draft. And then finally, it could revise and give me a final output of what I can post, for example, or use for marketing. So this is an example that we are going for. And if we look at the code, it's going to be really similar to before. So we have the trend research. Here we have the sequential agent having the trend, audience, and competitor. I don't think this is the right code, but I'll show you the right code in the code itself. Let's see. So we have the content orchestra right here, and here is the trend researcher, audience, competitor. Then we have, oh, it's actually the right code. Then we have the sequential agent running the trends first, audience, and then competitor. Then we have the outliner. So it goes towards here. Then we have the reviser, critic. Then we have the loop agent right here. And here is the whole orchestra, so to say. So we have the research team, which runs first, then the outliner, then the drafter, and then the refinement loop. So let's have a look at the execution of it. Let's say if I go to the agent example here, and then I go to content orchestra, And here I can say, for example, visual feedback on videos using loop.inc. And this is something that I'm building as a side project. So let's see how it does. So it's right now going to the trend researcher. And let's see how long this takes. Do we have the streaming available? Yes. All right, so here it's searching for the trends right here. And then now we have the audience researcher. And now we have the competitor analysis going as well. While this is happening, I also want to show you something that is not just in my machine, but actually is working in production. So this is my community, which is an online community. And I'm being right now followed by about 200,000 people on social media. And I have a community online for more than 5,000 people. So here we have an agent that they ask questions about. For example, here you can see a couple of people asking questions. So here I could go ahead and say, hey, assistant, who is an Angular mentor in the community? So what happens in my community is that we try to match mentors with mentees. We also have collaborative projects as well that people work with, and then also free courses and AI workshop as well. So here you can see that it has found the people like Nabil, myself, because I'm an Angular Google developers expert as well. And this goes through an MCP server. This has the same technology. The Google ADK behind the scenes has a bunch of agents that the root agent decides which one to pick from, depending on the question. It could also ask, or you could also ask, for example, if you wanted to find a repository or a GitHub repository that you wanted to contribute to. For example, which GitHub repos I can contribute with. And then you can say, I understand JavaScript or I know JavaScript. And this is great for freshers or people who are right now studying, that they can find those curated information. Aha. Okay. And it is looking at, anyways, I'm not going to debug right now in production, but yes, this happens. So everything was going right in the demo until this. All right. Now I want to see what is remaining, because there are some things that I also wanted to share. Yes. So one of the things that usually is a problem is we don't provide the output key. So it is really important to do that, otherwise your agents would not be able to find those. There was also a problem with Gemini 2.5 Flash. When you used Google search with a tool or a custom tool, it doesn't really work. Now with Gemini 3.5 Flash, it's possible to use that. It's in early preview right now or in beta, but you can start experimenting with that. And that means that your agent can do a Google search, but also use other tools as well. This was not possible before. And as I mentioned, when you're using a loop agent, you have to have a max iteration or exit loop as well. And when you're working with parallel agents, you don't really write on the same state key. That's also important. And your prompt, your description, your system instruction all have to be really explicit on what the agent does, and also the contract of the functions or the tools that are being returned as well. So what I want to leave you with is we have something called Agents CLI. It's not covered in my talk, but that allows you to create these agents even from terminal. So you can just give it some description and it generates those agents for you. It also allows you to deploy those agents to cloud as well. And if you're not using that CLI, then ADK deploy cloud run is the command that you would use, and this would deploy your agent on cloud run. You can also use this agent on the Vertex AI agent engine. Now it's called Gemini Enterprise as well, but definitely try that as well. And when you want to work with your own products, you want to add custom MCP tools. For example, how many of you know OpenBNB? Okay, no one knows. I did not know as well before. Like Airbnb, OpenBNB is essentially Airbnb, but when you go with Airbnb, there's a fee in the middle. For OpenBNB, rentals can opt in to say, we don't want to have a man in the middle, so it becomes cheaper for you. And they also have an MCP server. So if you add MCP server to your AI tool, you can just ask, okay, I'm going next week to, I don't know, Barcelona. Where do I stay? And OpenBNB will give you exact listings of that. And all you need to do is use this MCP toolset with your agent, and then it hooks that OpenBNB server with you. And you can also obviously use other MCP tools as well. And that's pretty much it. I'm going to show this again, and I would highly appreciate if you can give feedback. And I would end the session here as well, so you can give a comment as well. But if there's anything that you want to know more about for ADK, or how would you deploy them, how would you scale them, feel free to ask me. I'm going to be around for a while before I go. As you can hear, my voice is not really good today. So I'm going to stop speaking. But I want to finally end this by saying agents are not magic. So one of the biggest problems with companies right now is that they're using the same practices, but they're thinking that somehow the agents would improve and start fixing things for themselves. That doesn't really happen. They are specialized functions. So when you have the right prompt, the right configuration, the right workflows, then you essentially are able to achieve what you can. So thank you for having me, and this was fun.
Thank you, Mohammed. That was a beautiful presentation, and I was like always on my toes. Is it gonna break? Is it gonna break? Yeah, it was great. Thank you. I know that we have some questions from the audience, right? So if you can speak up a little bit, because I don't think we have a dedicated microphone. Or do we have one?
There's a mic here.
All right.
Hey, thanks for the presentation. I just had a question. This Google ADK, is it similar to something like Crew AI, LangGraph, or are these different?
Yes, you can compare them with the LangGraph or LangChain. Yes.
Yeah, and Crew AI.
Yeah, exactly.
Yeah. Okay, thanks.
No problem.
But this one's free.
It's Gemini is 60 requests per minute is free for most of the models. So if you're sending a question every second, then you're going to run out of quota. Otherwise, you won't.
No, but I mean the ADK.
The ADK is free as well. Yeah. It's free. And you can deploy ADK on Google Cloud Run with a Docker image, or you can just host it on your own. No problem.
Hello. It's a quick question about, because I'm new to agent development. So you are using Python, and I mostly work with JavaScript. So can I start with JavaScript?
Yeah, first of all, if you were close to me, I would be doing a fist bump with you, because I also am not a Python engineer.
Yep.
I work with JavaScript and TypeScript, and ADK recently launched the support for TypeScript. So now you can actually create TypeScript-based ADK agents as well. And if you have scanned it, you will probably find on my YouTube channel as well a video pretty soon about that, how you can create those.
Thank you.
Yes.
Wait a second. We need the microphone because we are doing this live session and people just don't understand what we're talking about. So, who has a question? Yeah. Thank you.
Sorry, this is more like general question. So, seems like you mentioning that there's a lot of agents with specific functions. When would you suggest people to create this specialized agent versus just use one very smart agent like Cloud Code agent or something, and just put different prompt, different scale, and load them on demand? Yeah. Thanks.
I think I would almost always go for a specialized agent over a normal chat. So I wouldn't want to just spawn an agent without any tool, without any specific prompt or instruction, and then just ask it questions, because it would be not specialized. It wouldn't know, and that is the context engineering part that comes in. So you'll hear this term called harness engineering quite a lot, which is essentially your agent plus the environment around it. So it's I think of it like it's a plant. So you have a plant, you have a seed, but then you also have to have the whole environment. You have to have the right soil, nutrients, watering, sunlight. If you don't give it, it won't grow. So that's similar to agents as well. You won't find it as useful compared to being a specialized agent. So even with Cloud Code right now, I have a specialized agent for SEO, for coding, for reviewing the code as well, and especially around the things that I do. For example, the slides that I showed you, I did not. These are all programmatic slides, but I did not write a single line there as well. I use agents to generate based on the topic that I have in my mind and some sort of sketches as well. And then I just generate the images. So specialized agents, I would say, would be useful in, I would say, 90% of the cases.
Okay, thank you.
You're welcome.
Any more questions? All right, good. Thank you, Mohammed, once again. That actually links with the first speech that we had from Ed, right? When he said that he is not writing code anymore, he's just wipe coding. So that's good. All right, moving to the next topic. When SQL breaks, you run explain. You get a query plan, you find the problem, you fix it. When vector search breaks, it fails silently. The results just get worse. And unless you know exactly what to look for, you will not notice any difference. Now, Simon here is the founding solution architect at CEST. And he's built a set of interactive visualizations that show you what's actually happening inside vector search system. Please welcome Simon.
Thank you. I also use AI to generate my slides, but just Claude because I'm not clever enough to use multi-agents. So what I want to do today is compress a 2-day vector search workshop into 30 minutes, ideally 28 minutes because we're running behind schedule. Who here is currently using a vector database in their architecture? All right, 1 or 2. So the good news is you soon will be using a vector database. I'm pretty much sure of it. In the next 12 to 18 months, there will be a vector database somewhere in your stack. The reason for that is over 95% of the data that's being generated on a daily basis in the world is unstructured. It's images, it's call logs, it's transcripts, it's CCTV captures, it's autonomous driving video feeds. These types of data don't fit into relational databases. They do fit into vector databases. I've been in the VectorDB space for about 5 years, and as Nick said, I recently joined Zilliz. I'm guessing no one here has heard of Zilliz. Has anyone, oh yeah, my TiDB friends, thank you. Has anyone heard of Milvus? Yeah, we've got a couple of Milvus fans, good. So Zilliz are the creators and maintainers of Milvus, which is the most widely deployed vector search engine. And the reason I joined is because it's Apache 2, it's cloud-native architecture, it's almost infinitely horizontally scalable, it uses LSMs for performance, so it matches all of the kind of... I didn't really understand what it was. I did actually study it in my master's at university, but I forgot most of that as soon as I left. One of the key obvious things is if you're doing a search for comfortable red trainers on an e-commerce website, keyword search, so Lucene, Solr, OpenSearch, Elasticsearch, will match tokens. It'll match the words that the user has put in the search bar, which means your first result is a perfect match. Great. And then you get red wine glasses, because red matches red. It's as a contrived example, but the key thing is with vector search, you're not looking at tokens, you're looking at meaning or intent. So red is similar to crimson. Trainers are similar to sneakers if the model's been trained on the right data set. So the whole of this talk rests on this concept that we're matching meaning. And that could be with images, could be with text, could be with sound. And the nice thing is, once you understand the right-hand side of this graph, the left-hand side is easy. Other people train models for us. You can get them off Hugging Face or Kaggle. The most important thing is, all this unstructured data gets run through a magic machine and outputs a row of numbers, typically between 512 dimensions and 3072 dimensions, which is the length of the array, of float 32 numbers. So that 4 bytes each times 1,000, 4 kilobytes for an embedding of an image. What can we do with these magic numbers? Now, some of these you might have heard of. Who's heard of RAG, Retrieval Augmented Generation? Yay! Who's heard of agentic memory? Yeah, if you use the memsearch plugin in Claude, that's using Milvus under the hood. But there's so much more you can do once you have this ability to query against semantics or meaning. Things like autonomous driving, understanding strange behavior in your autonomous cars, or screening cancer samples. So having a database of pathology samples, that means that clinicians can more quickly diagnose cancer and propose the right treatment. So there's so much cool stuff we can do with a bunch of numbers. Now, I wanted to bring this to life a little bit. So here is an array of 16 celebrities. If I wanted to build a model, when I got a new celebrity, throw it at the model, it could tell me who that face is closest to, or if it is indeed a celebrity. What kind of dimensions might I use to split these people up? Any shouts, any ideas? There's a pair of socks for the first answer. Gender, fantastic. You can come get your socks later. I'm not going to throw across the room. So I chose age first. So now I've got an x-axis of age with the youngest on the left and the oldest on the right. So now when I get a celebrity, I can roughly tell who's closest to them in age by dropping them on this axis. Gender was the next one. I went for femininity. So more femininity is good, less femininity is man. And then we can go by skin tone, for example. And now we have this clustering of people where we can roughly see who is closest by their features. Now, models aren't this simplistic, and I've terribly oversimplified it, because once you have 3 dimensions, that's pretty naive. When you have 3,000 dimensions, this kind of mental model of 3D graphs doesn't hold up. So I'm going to stick with 2D, because I can understand 2 dimensions. When we're looking for this similar celebrity, we need to measure how close that new celebrity is, that query, to the existing data set. Now, the most obvious one for me is L2, or Euclidean, which is literally just measuring the distance between points. In 2D, that's obvious. In 1,000 dimensions, a bit more maths is involved, but the logic is the same. The metric you use is defined by the model. So L2 is often used for visual search, similarity, like our celebrity use case. Cosine is generally used for text, and that's looking at angles. So whereas before we had a score that could be pretty arbitrary between 0 and infinity, cosine goes between 1 and -1. And then dot product, or inner product, uses the angle and the size. So you're always going to get on the outer edge in a plot like this. The trick is we would normally normalize the data, so cosine and dot product are about the same. But let's stick with Euclidean because I can understand it, and 2 dimensions. So the obvious thing to do is just take a query, stick it in, there we go, stick it up here, and run our search. If I ask for 5 close points, who here could immediately tell me what they're going to be? Oh, come on, you can do this. 1, 2, 3, 4, 5. As humans, we're quite good at finding visual patterns. Ooh. Computers are a little bit rubbish by default. Naive, brute force, exact, flat search will compare every potential candidate to the query candidate and say, I've got 5. I'll keep going to see if they're any closer until I finish comparing everything. Which is fine when you've got 16 faces to search, not fine when you've got 1 billion, 10 billion, trillion things to search. So everything we do in vector search is about compromise, which means we have a trade-off triangle. And again, there's not enough dimensions on a screen to really have a trade-off triangle, but I'm doing my best. So this flat exact search is extremely accurate, 100% accurate. But you will soon run out of your latency budget and your AWS budget if you try to do this at scale. So we need approximations. Now, if we're having approximations, we need to measure how approximate it is. And this is kind of the nuance of vector search is you never get 100% accuracy, but you need to know how far off you are. So if I search for movie with a robot from the future, who can guess what the first result will be from Wikipedia? Terminator, yes. But iRobot and the Matrix came up as well. So this is an open source data set from Kaggle using a naive text embedding model. And we can see we've got some cutoff here where there are Terminator movies that didn't make it into my top 10. So not bad, not perfect. What we can do, though, is measure how bad or not perfect it was. So recall at K says we asked for 10. Out of those 10, how many would be in the exact brute force flat scan? So we got 4 out of the 6 that should be there. So our recall is 0.667 or 66%. Precision is a bit more nuanced. How much of this was good? And this is really hard for you to measure qualitatively, but we can use recall at K and flip it, which gives us, we got 4 out of 10 of what we should have. So it gives us 40%. So if you see recall at K or precision at K, that's how they're being calculated. But what would happen if we filtered to movies that were released after 2000? What would that do to our recall? We'll come to that later. So the big idea is, can we trade a little bit of accuracy for orders of magnitude improvement in scalability to make this actually feasible? The first way to do it is to use IVF, not what you're thinking. This is inverted vector files, and the idea is that you drop your query somewhere in this space, and when you've built your index, you've sliced it into chunks, which are geometrically apart from each other, and you've measured a centroid for each of those chunks of vectors. So when a query comes in, you just find the chunks that that query is likely to be close to. But we're missing this one, and the right answer could be there. So then we increase the number of cells we look at. And eventually we get to a point where we're pretty confident we're going to have the right answer if we've got the right nList and nProbe. Now there's a lot here going on here, but there's really only two parameters you need to care about. nList is defined at build time. You can't change it. So if you get it wrong, it's a reindex rebuild. nProbe is tunable at query time. So if you don't get the right result, you can just increase the number of cells you're going to probe, go back and do it again. Generally, anytime you need to change something at build time, it's expensive and bad and you avoid it. Now, who here has heard of 18SW? Who can tell me what it stands for without tripping over the tongue? Hierarchical, navigable, small worlds. I have to say it slow. Oh, it says it there. Oh, you should have all put your hand up. So the idea here is that rather than immediately going to search everything, you have different layers of coarseness. So you start at a really coarse layer, which means you're only comparing a couple of thousand effective centroids like we saw in IVF. Then each layer down, you get more precise. So you start by scanning across from our query, which is the star, and you find, oh yeah, B is probably the closest. So you go to the next level and start from B and work outwards to see if there's anything closer. And yeah, F is closer. So then you move down to the next level, start from, oh no, E was closer, my bad. And you start from E, you work around, and eventually you find that this is the ideal point. Now, 18SW is complex. It lives in memory and is expensive, but its complexity comes with the benefit of recall. 18SW tends to be very accurate. Again, lots of things you can change. Really, the only thing you can change at query time is EF, which is how many candidates you hold in your hands as you're navigating through the graph. Most vector databases will automate the top two for you, but they might need tuning. DiskANN is the one I find hardest to explain. And I asked my TiDB friends yesterday if anyone could explain it, and nobody could. So I'll do my best. So this is designed to live on SSD, specifically locally attached NVMe storage, so high IOPS. You've got all your vectors on disk. Each of these is a file, effectively. Now, your medoid is the central point within that vector space, or the most central vector. When you start, you build a graph and randomly assign edges to nodes. You then go from your medoid and do a greedy search out to other nodes to build up a network of edges where you have the shortest trip between each node. And then you get some shortcuts thrown in as well to be able to traverse the graph really quickly. So you end up with something like this, and then we add the pink lines back, and it looks really messy. But this allows us that when we drop a query in over here, we can really quickly, with 4 reads to SSD, rather than 60 in this case, get the exact result we're looking for. And DiskANN is extremely good at very large scale. And again, this is just like 18SW, but with different names. How big the graph is, how many candidates you search for. So the benefits for approximate nearest neighbor, before we had this big O relationship, and if you studied computer science, you know big O is always bad, to a big O initially, up to about 7,000 vectors, where the graph architecture, no matter which one you choose, pays off to a straight line effectively. So you get this, the number of vectors can go up to trillions, and you're still only doing 10,000, maybe 20,000 comparisons, because you've narrowed the scope of the search. 5 orders of magnitude, 0.0001% of the total space has to be searched in a very large-scale vector deployment. Now, this is where it gets complicated, because I've only shown you a couple of ANN techniques, and there's loads. So we've got 18SW is the furthest away from cheap, because it lives in RAM, and if you work in cloud architecture, you know RAM is expensive. And then you've got ASAC and DiskANN, which are on disk. Disk is cheaper than RAM by an order of magnitude. So you can start seeing where you're pulling these levers to improve your cost-performance ratio. But this sounds complex, right? As most of you haven't worked with vector databases before, I've just thrown loads of acronyms, which you will forget within, well, after the first glass of wine this evening, I expect. Can't the machine do this? So there's 2 options. And this is kind of focused on what I do at Zilliz. You tune, you pick the right index for your use case, you understand the data, you understand the query patterns. You set your build knobs, you validate, you test, you run in production, and then you do quantization, which we'll talk about in a second. Or you use Zillow's cloud service, which is Milvus plus some sugar on top. Auto-index, you just say, I want it to be fast, and I'm using cosine, and it does everything else for you. What's really cool is that last point here is we segment data as it comes in, and you can change your build time knobs per segment. And then a coordinator ensures there's no drift between those different segment queries. Super cool. All right, I said we'd talk about quantization. We've got lots of numbers. Float 32, 4 bytes. 4 bytes times 1,000, 4 kilobytes. That gets big quick when you're in the billion vector scale. So can we make them smaller? Now, introduce a totally novel concept that I don't think anyone else has done before, but I can't visualize things in my head, so I have to get it on screen. So I've taken each embedding for each face, and I've turned it into a grid of colors where the hue is defined by the value of the dimension. So you can start to see there might be some patterns. Like here we've got this blue line coming up, and there we've got a blue line that's similar. And in fact, they're the two most similar faces in the dataset. And I think of this like genetics. Your phenotype for hair color isn't defined by one gene, it's defined by a collection of 20 or 100. The dimensions in the vector don't specifically say, this is for age, this is for facial hair. That was an oversimplification at the beginning. The model has trained itself over billions and billions of samples to understand how to differentiate the type of data it's getting in. And you get people who look different. They still have some similarity, like the little red hat at the bottom. I just think that's really cool. So that could be face shape. Okay, so how do we make them smaller? The obvious thing is just to round it. So we could take float 32 and round it to int 8, so that's 4 bytes to 1, 4 times smaller. If you actually do this and try to represent it as color, you've gone from 4 quintillion distinct options with float 32 to, I don't even know what int 8 is, lower than 4 quintillion. So you don't notice the difference. And in fact, Elasticsearch in version 9 defaults to int 8, and you have to opt out to get full float 32 because there's no difference. You can go further than that, though. You can go to float 16, brain float 16, int 8, int 4, and binary. Now, if you naively just rounded every number to -1 or 1, you're probably not going to have a good time. In fact, your recall would drop to about 40%. If we were in a 2-day workshop, I'd have 2 hours dedicated to RabbitQ, partly because the paper only came out last year, I think. But secondly, because the maths is insane. You have to project plots onto a hypersphere and do error correction and rotation. And I need to present it to understand it. The idea being, can you get rid of all of the loss of binary, but all the benefits of having it tiny? So 32 times smaller. By default, you get about 76% recall with binary. If you refine, so take your binary, take the results, oversample them, go back and refine at int 8, you get to 95% recall at 4 times faster or more throughput, lower cost than float 32. All right, now PQ is the weirdest one, and I do have a visualization for it, but I've hidden it because it's messy. So you've got 512 dimensions in an array. You split that up into 8 arrays. You plot them each into vector space. You do centroid mapping, so get 256 centroids, a bit like IVF. And then instead of storing the 64-dimension array, you just store the byte that represents which centroid that array was closest to. Now, you might see some problems with that. You get very low resolution, but you get massive performance improvements and throughput. The problem is that the codebook, where those centroids map to, is static. If your data starts to drift, your PQ goes wrong and your recall drops. There is another thing called PRQ, which is product residual quantization, which stores the error with each vector embedding, which makes the recall and resilience a little bit better. But I don't have time for that. The funny thing is, even going all the way to 32 times reduction in footprint, you don't lose a lot of recall. PQ is the worst, but RabbitQ and purple up on the top right is good, gives us so much benefit in terms of storage improvement at little recall cost. So let's throw one here. It's just arrows pointing towards cheap and fast. So there's lots of levers we can choose, or choose to use. Now, if we've made the numbers smaller, can we get fewer numbers? Who studied principal component analysis in school? Yeah, a few people. Quite a few people. So the important thing is no one does this in production. LIDB from Google is the only vector database that actually does this because it's a bit rubbish. But the concept is good. So you take these two clusters of data. We're in 2-dimensional space, right? You identify your principal components, which are the lines along which the data varies. Identify the one with the least variance, and squash it. So now you have one dimension that you need to store. And you still get 94% of the variance between the two types of data. The problem is that blue and purple bit, the separation of those two clusters is lost. And that's why you don't really do PCA in production. What we can do is Matryoshka. Bing. Named after the Russian nesting dolls. This has to be supported by the model. Has anyone here used text embedding 3 large? It's OpenAI's latest bleeding edge text embedding model. So it is 3072 dimension natively, which gets really expensive to store at big scale. One PDF might have 1,000 chunks. Each chunk then has 3,000 dimensions. At float 32, you can start to see you're going to run out of RAM very soon. What the Matryoshka representation learning model does, MRL, is takes the most important dimensions and puts them first. So if you chop everything off after the first 256, you still get 96% recall or variance within the data. And the really clever thing is you can store both. So you can store the vector once, do your first query on the head, the first 256 elements, and then refine on the tail of the vector to get almost perfect recall at very little cost. So that just pushes everything towards fast and cheap. Now, fast and cheap is good, but sometimes we do want accurate, and it's nice to have a lever that you can pull, not all the time. Maybe just at query time or when your agent's really struggling, or you've got a really important use case and it has to be perfect. This is where refinement or overscoring or resampling really comes into its own. So you've got your quantization binary. You've reduced the number of dimensions to 1. You've got everything represented by 1 or 0. You do your first pass, and you've got half of your data set returned. That's really fast, but not very useful. If we extend that concept to, let's scan 1 bit with RabbitQ with 1024 dimensions, you're going to get reasonably close. You're going to get 75, 80% recall. So you oversample, get the first 100 when you want 10. Take those 100, rerun the vector search at int8 or float 32 to get your real precision. But you can do that brute force because it's such a small number of embedding calculations to run. In Milvus, we have a build time flag, which is refine true. And you say, I want binary quantization refined to int8 or float 32 or whatever. Then you tune refine k, which is how many you want to oversample by. And then every time you run the query, it does that out of the box. That's in open source. It's free to use and play with. You can install Milvus with pip install PyMilvus and play with it. You can do really clever things with this as well, like building a lightweight index on top of external data. So if you had 500 petabytes of data in S3, you don't want to index all of that into another tool, another service. So very recently, we launched Vector Lakebase, which allows you to build a lightweight index on top of S3, and then automatically run through this binary quantization to make the most of the data that's already there. So refinement pulls us the other way, and that's query time. Now, I asked you to think about what happens if we filter that query to movies published after 2000. This is hard. So this is one of the new Terminator movies. I assume Arnie was in them after 2000. In SQL, this is pretty simple. You have to decompose it into your filters, but in vector search, it's really tricky. Generally, you have 2 options. One is you pre-filter. So you get a bitmap, which nodes in my graph will match this predicate, and ignore the ones that don't. But that degrades the quality of the graph, so you might end up in a bunch of local maxima and miss the actual result you want because it was disconnected because of filtering. Post-filter is you say, give me 1,000, then apply the filter. And I'm only asking for 10, so that should be fine. But if you have a very selective filter, you might end up with 0 results. Neither of these is great. So what we try to do is we try to do 3 things. If the filter is very selective, so there's only 1,000 embeddings left, just go straight to brute force. Take the ones that match the filter, brute force it, you'll get your top K. If it's not selective at all, so 99% will do it, then you do post-filter. And if it's somewhere in the middle, you do graph or filter-aware graph. So use Acorn or Alpha, and you don't have to remember all of that. But it just means that you don't remove the nodes from the graph. You understand what likelihood there is that a node will reach a node that matches your predicate, and keep those nodes in. All right, when retrieval quietly fails, and this talk was all about explain, there is no explain for vector search. In SQL or Lucene, you get explanations. You get stack traces, you get logs, you get errors. When vector search goes wrong, you just get no results or the wrong results. There's no plan, there's no reasoning. So what can we do? I think the most important thing is to understand what you expect to see, and then every time you make a change, validate that you still see what you expect to see. So you take your golden query set, maybe 100 or 1,000 queries, you run brute force exact search, get your golden result set, and then compare that with a production vector search. Then you get your recall. You can do it in level is in Zilliz, not in Milvus. Enable recall calculation is in both. So when you run your query, you turn on this flag. It will run the brute force at the same time as the ANN and give you a recall figure in your response. Don't use that in production for all queries, because it is expensive. But you can use this whenever you need to validate recall. Now, if you're using agents with vector databases, this will be, I don't think you are, but the assistants get dumber because it's not able to reach the memories it needs. So we need to measure before the agent gets the data. So that's just going back to measuring recall at K, measuring the score spread, your hit rate on filters, and making sure that you're not giving the agent stupid data. So two things here are refinement and semantic highlighting. We talked about refinement. Semantic highlighting is where you use a second model with your vector search results to refine just the bits of the results that the agent will need. So that can massively reduce your token count. That's cool. All right, so just 5 strategies, and that's it. Use the right index type, experiment and play. Use compression techniques where it makes sense. Query time levers are the best bet for making any change. And then measuring recall is the most important thing, which is both those last 2 points cover the same thing. Right, and that's it. Thank you very much.
Thank you, Simon. That was beautiful.
Thank you.
Any questions to Simon this stage? We're not touching the socks part?
Nope.
Should I ask this question myself?
If you walk along the stage like this, it bangs.
Oh, you see how nice people are, right? I haven't even thought about it. I was like an elephant here, all the time. Where are you from originally?
I'm from London.
From London.
UK.
Okay. I see. Real queen etiquette.
Oh yes.
The most sophisticated one. Talking about nice people. Apparently, people from there behind the stage heard that I was saying good words about local buns, Swedish buns, and they prepared a new bunch of buns for me, and I want to share it with you. So let's take another coffee break, 10 minutes, and then I will welcome you back here. Thank you. Hello, hello. Oh, okay. Awesome. Yeah. Right. If some of you developed an unhealthy relationship with a bun, you can take it inside with you. You see, I have this special attachment to this pastry. Now, I hope everyone had enough coffee for today, and let's move to another session. I will start it with the phrase, duct tape. That's how Bernard describes the architecture most AI agents run on today. Separate systems for transitions, analytics, and vectors stuck together with brittle ETL pipelines and a lot of optimism. Bernard is a principal solution architect at TiDB, and today he is making the case for I'm sorry, this bad. Making a case for different approach. Please welcome Bernard on stage.
Thank you, Nicholas. Cool, man. I could have finished that bun for you if you want me to, but...
No, that's fine.
Yeah. Thank you very much. So yeah, my name is Bernard. So I come from a background of data and analytics. And I've been working at TiDB with PingCap here for 8 or 9 months now at this stage. But I can't tell. It seems like a few weeks because it's gone by so quickly. But yeah, today we're going to talk about a little bit of a gap that exists. So everybody here is familiar with the idea of agent memory. So we've talked about vector stores, we talked about databases. I think by now you're familiar with the strength of TiDB. So I'm going to talk you through a real life use case and what attracted me to come and work with TiDB. So the remit of AI hasn't really been defined yet. A lot of people talk about what their data should look like or put agents on your data. but a lot of people are using agents for Gen AI, for slides, and you might recognize the font from Anthropic and Claude here. But your data, as it is right now, is meant to be looked at as opposed to be acted on. So everybody says about, in analytics, they talk about real-time data, they talk about data action and take action on your data and so on and so forth. But in the world that I'm aware of, real-time is a promise that hasn't actually been delivered yet. So if you think about the thousands and millions of actions and events that are generated from applications, from payments systems, from sensor data, IoT, network telemetry, there's billions of events that are occurring out there. So when you try to move that data via Kafka or Flink or wonderful systems like that, it goes into a lakehouse and it goes into another proprietary system where you need to use things like dbt, then you need to shape your tables, then you need to run queries against it, then it goes to a dashboard, or it goes into Excel or Google, or so on and so forth. So there's numbers and numbers of steps. So that's what the duct tape piece that Nick was referring to. So we call that the Frankenstack. So you think about the world that we live in, or have lived in for the last 10 years. The stack is built for BI. So business intelligence, but there's an army of analysts out there. So there's not really a problem with the logic. There's not really a problem with the dashboards or with the visualizations. It's the things that people want to do with that data. But now in the world that we're moving into, there's an opportunity to use autonomous agents with very strict guardrails, or agents plus sub-agents, etc., etc. And I think you know where we're going with this. We have to add things like, we're missing a box somewhere on that one there. It should be 3 on it. But we're talking about the gap that exists between, there's a third one in there somewhere. The gap that exists between the stack that we have right now and what's going to happen. So you need to add vector databases, you need to add embeddings, you need to do cosine distances. So I read last week about the threat intelligence report that was published by Thales, by Fortinet. So I read down through it and I aggregated it. There's 85 brand new metrics and cyber threats based on events that are now present with agentic workflows, because hackers and malicious users can send millions of requests per day. So things like stuffing, carding, all these words that are kind of brand new in the agent ecosystem. These are threats that our customers are going to be dealing with, and you yourselves are going to be dealing with very, very soon. So it says agents are stateless, but LLMs inherently are stateless. Context stuffing is really difficult. Agent loops are very expensive. Tokens cost money. And the more systems you add on, the more infrastructure, the higher your bill goes. So the data is moving, and it's moving. So we're going to talk about a company that we worked with. They're an EV charger platform. They have IoT data. All of their chargers send sensors through. They ran this on the analytics database or warehouse they were running on, and the initial, they call it the $50,000 bug because they couldn't figure out where it went. They tried it for a day to automate their fleet maintenance system. So error messages come in from the system, they window it with Flink, they look for autonomous scores, they give an anomaly score that lands in TiDB or in the system they had, that generates a vector embedding, there's sync lag between it, and the agents they were running were just continuously in loop. So one day test, $50,000, they said they don't want to do it. So they want to scale from 20,000 chargers to 100,000 chargers. So it's a 5x growth for their business. But they also want to be able to sit in front of any of the procurement teams and say that we have the highest fleet maintenance, we have the highest uptime, the most modern, automated, autonomous fleet maintenance system that they have. So we ran an A/B test with TiDB versus what they have. So they had vector stores, they were using Redis as federation layers, they had their normal databases, their transactions, etc., etc. So when they solved, or they optimized their 50,000 bug, they reckoned it was going to cost them close to $130,000 per month to run this. So then we went and tested it with TiDB. And as you'll know by now, vectors are a data type inside TiDB. There's no session cache. There's no separate analytical warehouses. We're optimized for read and for write. So meaning that once there's a trigger to say there's an anomalous row, that can then go ahead and trigger the orchestration queue for an investigation to occur. Given that TiDB is a single asset engine, that means we can run a single SQL query to see if we have a defined semantic memory of something that exists beforehand that allows us to route the model to a cheaper version. And we can have confidence from a cold start that started at 74%, but on average, a confidence score from the agentic investigation of over 90%. So if we move on to the next slide. So if we look at just 21 peer-cited, that's what it took for its warm-up. So 21 investigations before it went from cold to warm data. And then their context score and their tokens cost actually began to go down. So a cold start starts at 74% and then up to 99. So an average of about 93% confidence. So we were working with, or a friend of mine actually, it's more of an anecdote, who lives in Dublin. He works for Notion, and they're building coding agents. And they're trying to, if you imagine a customer that works for Notion or has Notion, you have to access maybe Drive, OneDrive, Jira, Slack, various systems. So again, kind of fragmented context or multiple systems. And they anecdotally told me they cannot get a confidence score above 60%. So if we look at the story, so the cold cluster versus a warm cluster where the confidence went, you can see that we had the same model, the same telemetry, the same prompt. The only difference was we had a single system instead of multiple systems. So to go back to where we started, we wanted to talk a little bit about the existing data stack. So it's an analytical stack. It's built for BI. We're now adding on things like vector stores and other pieces of infrastructure, plus orchestration layers, plus agents, plus sub-agents. So in the world of analytics, or analytical agents, or functional AI, as opposed to generative AI, think about the volume or the potential that exists within that. Hundreds of thousands of investigations or SQL queries that are run against a database on real-time data. So now think about how we can address the idea of the cyber threats that are growing and occurring, about the event mechanisms, about how we can follow mouse clicks and patterns, and how we can have, it said in the report last week that they need to have a cosine distance of under 5% to tell the difference between malicious actors and real actors. So in order to achieve an outcome like that, it's quite simple. We don't believe that it's going to be possible on the existing stacks. So which brings us to the workloads that warehouses simply just cannot handle. So real-time agent inference, they can't have hybrid semantic search, single query root cause analysis, i.e. what data did the agent get when it came to this outcome? So if you had a harmful outcome or an hallucination, which could be possible, you have to ask yourself, what did the agent see? So if you're dealing with the EU AI Act, so you have high-risk data, so anything that's public-facing, anything that's to do with fintech or payments, fraud detection, anomaly detection, couple that with any of the other ML flows that you have. Again, if you're across what we call a Frankenstack, essentially it's just not going to work. Your costs are going to go through the roof. But we also know about things like data monetization. We know about embedded analytics. We know about cyber threats. We all have cybersecurity companies. They want to feed that analytics back to their customers. So the margin for that data monetization is going to die in the stack. So every system boundary is another consistency gap between the analysis that the agents are going to look at. It's another authentication protocol that your security team have to look at. It's another component in your orchestration layer. Every sync job has a cost because they're not fully in line, because it takes time for the data to move between them. And any unjoined audit trail is potentially a liability, particularly in high-risk industries under the EU and AI Act. So now that we know about the data coming in, now we know about the problem that we're trying to solve, how do we maintain it to keep that confidence high? So given the fact that we could just run single SQL queries against everything, we've introduced 5 custodial duties that are really important to ensure that data remains high quality. So an engineer's job is not under threat in this world. A lot of people think that AI will take our jobs. It's actually the complete opposite. In the world of data, the volume of information is now growing exponentially. The volume of analysis is growing exponentially. The look back, the observability, the visibility, the traceability is growing exponentially. So the quality of data input and then the ability to look at high quality outputs that actually puts the engineer on a little bit of a pedestal. So in TiDB, given that we have one of the best engines that are out there, we have 5 custodial duties, so we have write control. So we don't write every ephemeral reasoning step an agent needs to do. We can look at tool calls. We can look at individual steps that were came, but what we really do is we just write the outcomes. So are things confirmed, escalated, deferred, flagged for review, etc., which keeps the human in the loop. So anyone playing AI bingo today, that's one of your first in the scorecards. The second is deduplication. So there are going to be similar outcomes because error messages come in more than once in this system, for example. So we look at things like cosine distance. We found that about less than 15% on a merge, which allows us to do compaction, which goes at the bottom. So we have lots of similar memories. So instead of having lots of vague ones, we compact those into really strong memories, which increases the confidence of the analysis. And then we can obviously reconcile that data, and we can avoid what we call confidence decay, because the more context you have, the less secure the outcome is going to be. And we've got that in our tests that we've run with our customers. So one cluster, no sync jobs that sits between it. So in this particular customer's scenario, the 20,000 charge points, 112 million events per day. We were able to write that down into 8 tables with 9 specific agent tools, and then we were able to put a token budget of 3,600 per investigation. And we were able to maintain that via model routing. So a concept of model weighting, is anybody here familiar with that? Yeah, Zilix will be, of course, the pioneers here. But model weighting is, you know, Opus versus Sonnet versus Gemini Flash Pro, Llama models. They have different weights and different costs per investigation and invocation. So again, if you want to control the growth, the scale of it, it's going to become a really, really serious topic for people to become familiar with. But to keep with the theme of the Frankenstack, we talked about the different systems. We know about our analytic warehouse. We know about our caching, stores, our OLTP databases, our vectors. You imagine an agent has to connect to each one of those. We talked about the auth protocols. How many loops does it have to get the particular context it wants to see? Where's the join going to occur? How do we stuff the context? Then you have to cache it. And everybody you've seen, every database vendor or data vendor out there talk about building memory for agents. A single unified substrate. Well, as it turns out, an OLTP or distributed database with the ability to read and write at the same time is the perfect system for that. So a single cluster, your data plane is your normal data input, your telemetry data, your event data, your payments data. The context plane is where the agent writes back to TiDB in the same schema beside it in an ACID boundary. So that means that the context assembly is done via a SQL query before it hits the LLM, so no loops. And that's what gives the confidence score. Alrighty. So how does TiDB make it possible? Unified hybrid transactional analytical plus a vector engine. So essentially semantic search. We use vectors as a data type. We can allow agents to use branching on our database, which means we can have safe sandbox tests with human verified outputs that stay away from production. So an engineer wants to check the quality of an output, they want to change the rules, they want to test the guardrails, they've got a safe place to do it without having QA. So the time to iteration grows or shrinks exponentially. And then obviously elastic auto-scaling on AWS infrastructure, which is going to be a nice segue to our next speaker here as well, who's a very special guest we want to introduce you to. So, I've got to fly to my last through 2 slides before a few questions. But yeah, serverless branching, hyperelasticity, and safety-first autonomy, they're the things that you get out of the box with TiDB. They're the things that you're all going to be very, very familiar with. And again, the pattern is actually generic. So we've open sourced the context plane code for everyone to use so you can test and iterate. And we want people to branch. We want people to open pull requests on it. We want to hear your opinion. And the more eyes that are on a project like this, the better it's going to be. So we want everybody here to download and clone those repos, run it on your TiDB, instances, do the testing on it. We'll provide you with the scripts to seed your data, and we want to hear your feedback on it. So all of these things here, my GitHub is github.com/Bernard Kavanagh, which is on the slide somewhere, I think. So you can essentially install any one of these on your TiDB cluster. And for anyone who doesn't have a TiDB cluster, you can click this QR code now and sign up for free. But given the audience, I think you're going to be familiar with TiDB. So please, come to us afterwards. I'll send you those links, and I want you to test them. We can set up some time and have a chat about it. And I want to hear your opinions on how these things work as well in production, because we want to grow these use cases. We see the growth of the cyber attacks. We see the different types of events that are coming through. And the more that we know from the industry, the better these solutions will be, and the quicker the industry can adopt them with your expertise. So that brings me to the end of my slides. My name is Bernard, Solutions Architect at TiDB. And if anyone has any questions, feel free to ping me at any stage. So thank you very much.
Thank you, Bernard. That was beautiful.
Thank you.
I almost cried in the middle of your presentation.
It's gorgeous.
It's so beautiful. Talking about beautiful things, right? It's 2026. We will live in a world of AI. AI is dominating every discussion, every technological discussion. Agentic patterns in the software development lifecycle are widely discussed. However, agentic patterns in SaaS operations almost entirely ignored. Now, Frederick is a solution architect at AWS, and he claims that running your operations with agents gives you immediate advantage over your competitors. That's a bold claim, Frederick, but we are ready to hear you out. Welcome on stage.
I got it?
Here's a second. Technical complication here. All right. I guess we're going to have a couple of minutes. Now, do you have any questions regarding TiDB right now? I will try to answer on spot. Challenge me. For free. For you, my friend, for free. Today. No, actually, Bernard just shared a QR code, right? So if you're interested in the DB, if you never had a chance to try it, you can run it. We have a cloud offering, which is free tier. You can run several instances there, see how it goes, try it, make sure that it fits your needs and everything. And I don't know, as Tarmo said, it will take you 3 days of vacation to know everything you need to know about TiDB to run it in your organization. But just to get a feeling, you will need, I don't know, maybe 30 minutes to spend. Just go on TiDB.com, pincap.com, whatever. It will redirect you and try it, spin it, try it, get a feel of it. That's amazing. That's regarding the price. Next question. Yes? Do we do content collaborations? We have Patrick here somewhere. We do. Yeah. We do collaborations. Gladly. Gladly. All right. More questions? Do you know how old PinCap, the company behind TiDB, is? Any guesses?
10 years old.
Close. Close. No, further away. It's actually 11 years. We turned 11 this April. Big date for us. 1-1. It's a like symmetrical number. I like it. It's a prime number as well, so I like it. You ready? Yeah. All right, Frederick, please welcome on stage. Here you go.
Oh.
This is for you. Do you need this?
Right, I will definitely be needing that. And thank you for keeping the stage warm. Last minute technical issues. Let's see if. All right, yeah, there we have it. So I'm excited to be here today because this is sort of my favorite topic as of late. Because I really feel that operations have been underinvested into. It's sort of been treated as this part of the organization that just keeps the lights on. The product teams get the budget, and operations get the leftovers. And I will want to argue in this talk that perhaps the real unlock with AI is through operations, because operations sit on all the data. Okay? My name is Frederick. I'm a solutions architect at AWS. I work with software companies, hence the narrative around SaaS. Okay? I will try to keep the SaaS speech down to a minimum to sort of capture everyone in the talk. And if you're not running a SaaS application or working with SaaS software, I'd still sort of argue that this is relevant because, well, the learnings are really applicable to anyone running operations at scale. That's sort of the pitch for the talk. And as the introduction sort of alluded to, what we've seen here is, over the past few years, a lot of experimentation in the software development lifecycle. Every few months, we have to upskill, reskill, rethink how we ship and deliver our code, right? And as of late, we've seen a lot of experimentation in invention on the end customer and products and services side. I'll still argue that we're far from maturity, and that's probably what this whole economy is about. What is eventually that full value that our customers are really going to see from AI? But I hear no one really talking about operations. What can operations do if we enable them with AI? Okay? Enough talk. Let's sort of dive into it. And we'll see also towards the end how TiDB sort of fits into this and sort of helps deliver upon this sort of promise. Okay? So, you built your SaaS. You have some type of application. You even have some users. Should be there. That's interesting. We'll see what. And you're perhaps also, hopefully, yes, making some money. If this is you, I think you should be proud of yourself because most people don't make it here. Okay. So, but what's next, right? It's sort of implicit. We all want to grow. Okay. How do we grow that revenue? How do we grow those earnings? Well, there are a few different ways. We can add more customers, achieve that linear growth, right? And we can sort of also add more revenue per customer. Perhaps we try to increase our value proposition to justify a price increase rather. And finally, we can try to be more resource efficient, getting to keep more of what we make. Okay? And these are not independent variables. They play off each other in interesting ways, right? So, but these are essentially levers that we have to our disposal to pull and push. And when our business objectives really comes down to any of these, and then the question comes down to, well, how does operations support the business in achieving this? Okay? And I go over some examples here, but it's by no means an exhaustive list. It's sort of what I perceive to be digestible in this context and some easy pickings in sort of the agentic era. Yeah, okay, there we go again. Customer insights, nonetheless. So, how do you go after new customers if you don't know who your current customers are, right? Perhaps all your customers coming out of a certain region of the world, and do you know that? Do you know what they value? And this is my favorite example. Perhaps what you thought was your core value proposition really isn't. Perhaps it's that niche feature of yours that you're not really paying attention to that's actually driving customer adoption. And perhaps you should pivot your entire business model. These are the sorts of things we get to through our data, okay? Oh, it's going to go through. Anyhow, cost visibility, I'll argue that once you have the usage down, it's not that big of a stretch to get to cost insights. Because if you have the usage data and you cross-reference that with your AWS bill, you have the ability to answer certain basic questions, such as, what is my cost per serve? What is my cost per tenant, cost per X, right? And why is this important? Well, naturally, how do we make investment decisions if we don't know what our margins are? Okay? Perhaps we even have customers that are unprofitable for us. Perhaps we need to push them up our usage tiers. So this is quite naturally important once you stop to think about it. And the final dimension here that I want to focus a little bit on, how operations support the business, is efficiency. This is perhaps the most obvious one. When you say, how does operations support the business in achieving its goals? Well, obviously, by being efficient with its resources. We don't want to over-provision our resources, eating out from our margins, right? But we don't want to under-provision our resources, degrading our customers' performance. And this becomes important, especially as we grow, because when you start out building your application, and this goes for everyone, you just want things to work, right? You're not starting out building an application thinking about efficiency. But as you scale, those inefficiencies that are inherently built in the beginning, they will scale with you as you start to scale. And the best of breeds, they know this. They have this covered. So the best of breed SaaS vendors out there, we all know them. I don't need to mention them by name, but they're under the 17th seed round, right? They have just made that huge, amazing, successful IPO. And I'd argue is that the reason they're this successful, or part of it as well, is because they have this understood. They know that their data is a core piece of their revenue growth. Because as you grow, and you perhaps start using your data to achieve that small, another digit percentage of growth, after 1 year, after 2 years, it perhaps won't matter. But if you keep reinvesting that, you'll eventually start to see the compounding effects. And all of a sudden, you're a different company. And now you have become the disruptor, okay, as opposed to being the one that's being disrupted. So this sounds all very important. And it really boils down to the concept of data strategy. And I really wanted to keep this slide for that reason that far too often when I speak to customers, colleagues, peers in this industry, this word seems to be somewhat difficult to grasp, and it really doesn't need to be. Because data strategy is simply how we go about achieving that critical key business outcomes, or how we go about answering those critical key business questions. And how we do that using data, that is our data strategy. Not to conflate that with technology, okay? So that is why I have this pyramid as sort of a mental model, that data strategy is downstream from your business objectives, but above technology. Okay, simple, yeah? So that's actually how I perceive AI in this. AI is just another technology. In this context, it's perhaps a bit reductive, but it works, okay? Because occasionally I find myself in conversations with customers. They come to me and they tell me something along the lines of, hey, help me. I want to get started with AI, but I don't know how. I want to get started, but I don't know where to begin. And if this resonates with you, I'd argue that this is indicative of you lacking a strong data strategy, or at the very least, you're working in an organization that has a poorly communicated one. Because if you have a strong data strategy, what to do with AI and how to leverage your sort of data is sort of self-evident, and you won't need me to tell you that. Yeah? And this is in particular interesting. Why aren't we all doing this? I've now argued for nearly 10 minutes here the importance of data, right? And the data topic is not new. Okay, I would argue that for 2 decades we've been doing this. And why aren't everyone a successful data-driven company? And this sort of slide, I believe, tells part of the story. And if we go back to the beginning of the talk, I talked about usage, understanding your customers, with like, who are your typical customer personas? That is, if you think about it, it's an unsupervised clustering machine learning problem. Okay, how do I identify some customer personas? Okay, if you think about that task, it's fairly difficult. It requires some pretty advanced ML ops, data engineering efforts, machine learning engineers, data scientists, all very expensive resources and competencies. So there's been, and I love this quote, let's see where you are. Cost of curiosity. The cost of curiosity has been really, really high. There you are, yeah. And with AI, we can really lower that bar of entry. We can sort of play the same game as the best of breed SaaS vendors. We can level the playing field, bringing down the cost of curiosity. So, how do we get started? Well, in a SaaS context, at the very least, you have some type of control plane. Okay, you have your data. This is the sort of application logs, metrics, traces, usage. You have tenant metadata. And I'd argue that if you take your agentic helper of choice, I'm from AWS, so I have to suggest Kiro here. So if you take your Kiro agent and you hook it up to your data tier, okay, using MCP, and also maybe even Cost Explorer, and you start doing that very basic exploratory work. This takes about an afternoon to get started. And especially with TiDB, if you're using that as your one-stop shop, database for your database workloads, it's even easier, right? So this, if you take away anything from my talk, it would be this slide, okay? Really do get started. And if you don't find something in your data, I mean, big deal. You invested like an afternoon. That's not a huge loss. And perhaps you learned something, so I'd still argue that it's worth doing. But if you do find something, that is when you bring something forward to your product management, to your leadership, or whoever, okay? But all right. We found something in our data, let's say, to continue the talk here. How do we persist that? How do we make that permanent? Because obviously we can't run from our local laptop like this, okay? So we'll see here there are some architecture patterns that will keep reappearing. And to build an agent, hopefully using the cloud, we'll see that there are eventually some building blocks that will keep reappearing. First of all, we have the brain, right? The LLM to start with, the reasoning capability. We have the tools, set of methods, right? These are the reliable, deterministic sheep actions that the agent can take. Well, that worked, yeah. Maybe PingCap has something to do with this. Anyhow, so a database. Because the agent needs data to consume, right? Also, perhaps the agent has some type of output and we want to persist that. And I also want to highlight this point. This is where the HTAP capability really fits nicely into this, because perhaps the input to your agent is more of a transactional type format, and the output is more oriented towards analytics, for the OLAP paradigm. So HTAP really fits really nicely in here. Gateway, you want to expose this, enable multi-agent workflows. So let's see what this can look like. We're using a real example. Let's see here if we're trying to build like a usage insights agent. Again, tying back to that sort of understanding your customer's sort of story. And for me to do this, I'd like to work backwards from some type of output. Okay, what is this agent intended to create? Okay, let's say we're trying to create a matrix, something that looks like this, a consumption matrix. What is a consumption matrix, you say? Well, along one axis, you have your tenants, right? Tenant 1 through n. And on the other axis, you have their usages as metrics. It could be your CPU usage, your memory, your storage, or a custom metric of yours for your business that is important to you. So if we have a usage agent that is creating this as an output, that can going forward be the basis for answering questions around usage. Okay, this is the source of truth now. And we create this matrix on a cadence, so perhaps this is a snapshot for the last hour or last day or whatever fits your business, okay? So how do we create this matrix? Go back to the agentic building block, okay? We define a set of methods. This is just conceptually speaking. I created a set of methods in my toolbox. These are perhaps needed in order to create this matrix of ours and persist it into our database here. And finally, also expose it to other agents. And maybe, and don't forget this, we still live in a normal world. We can just make normal database lookups, right? So what about multi-agent workflows? So this was one agent. Let's say you move up a step in abstraction level. Let's say you're trying to create another agent here. Call it a persona insights agent, okay? This persona insights agent is perhaps, excuse me, intended to answer questions like, what is the cost per persona based on feature usage? Okay? This question is composed in such a way that perhaps we need more than one agent to answer this. And this is something that we'll discover as we work with agents, that we'll see context boundary drift. What really fits into one agent and what should be split across multiple. And that's sort of your job as an engineer to sort of find that sweet spot, what suits you in those circumstances. But in this case, we have a usage agent and perhaps also a cost agent. So the question, what personas do we even have? Again, tying back to the usage, that's a question aimed towards our usage agent, naturally, right? Secondly, what is the cost per feature? What is the cost per feature? So that's a question for the cost agent. And this this is now sort of fed into the persona agent. They can now continue to answer questions along the lines of which of these personas are the most profitable. So we can now perhaps say, hey, let's target these customers of ours even more effectively. Maybe also, do we have any unprofitable customers? Okay, maybe we need to force them up a usage tier. This is again tying back to that strategic importance, right? These are important questions for your business to be able to answer. Now, there is one last thing here that I sort of deliberately left out, and it's sort of the agent state. We have here actually a cross-agent state problem, because the cost and in the usage agent's output is sort of like the intermediary reasoning step for the persona agent, right? And we need to store that somewhere, and that's also where TiDB fits into the picture. Because what happens if the persona agent crashes? Do we need to rerun those questions? Okay. What happens if you ask the same questions next week? If you do this on a cadence, we might want to compare answers. Or auditing, your manager pushes back as you declared one persona unprofitable. You can go back and sort of check that reasoning steps, like how did we end up here? So TiDB solves this for us, and it makes it ACID compliant. So naturally, we don't want our reasoning to be done on corrupt data. Okay. So I think this is, to me, sort of what wraps up this talk. It's just 20 minutes. It's intended to be a little bit thought-provocative, to really, again, highlight your operational data is of critical importance. And with sort of small, easy implemented agents like these ones, we can actually really get started. And if I want you to, if you can, remember one slide only, it would be that Kiro slide, how to get started, how to really build that initial momentum to keep going. Oh, I'm starting to lose my voice. So, call to action, go build. Thank you. I'll be around here for another hour or so. Otherwise, add me on LinkedIn, let's connect. Cool. Thank you.
Thank you, Frederick.
Thank you.
Yeah. I like your approach. If you want to learn something, if you want to do something, just start doing it right away.
Yeah,
right?
absolutely. Yeah.
Doing is the best way of learning.
It is, yes.
Yeah. So, yeah. Go to TiDB.io and start learning TiDB, right? Immerse yourself into the world of the best database in the world. That's what I want to say. Before introducing our next speaker, Alex. Alex is a technical sales professional at Ververica. Sorry. And today he is showing how Ververica and TiDB work together to give AI agents what they actually need in production. And this is fresh data, trusted context, durable memory, and the ability to act the moment a business event happens. A real-time AI, not as a concept, but as a working system. Please welcome Alex.
Thank you. Thanks so much for the introduction, and a big applause for this audience for support a whole day here. Okay, if you are waiting for the happy hours, we're that close. Okay, so my name is Alex Campos. I'm a solution engineer at Ververica, the company that is offering a Flink, Apache Flink solution, enterprise solution for customers around the world in different industries. Okay. Today, as more and more AI is pushing the boundaries for the companies, now why not to take the step forward and have these agents in general real time. Okay. So let's go through this presentation, and I bring a more practical approach on how to implement this in for real life use cases. Okay. Good. So AI is not just a LLM core. We all know that, right? This is just one part of the architecture. The whole architecture. It can be your internal LLM that you train, you fine-tune yourself, or it can be an external one like OpenAI or Cloud or others out there. But this is one part of the architecture. What agents really needs is more than that, right? They need fresh data to take decisions, right? So instead of context that is stale or from, I don't know, 1 month ago, which doesn't make sense, right? They need fresh information to take decisions, trusted context as well, everything related to customers, interactions, payments, how they use our platform, and so on. They also need this context, trusted context. Of course, we have a new source of data in our organization that are the agents, right? So now the agents, they also generate information like memory, right? We need to also capture and store and securely make it available for the entire company. And also the ability to act as soon as possible, right? So this is what when we have an opportunity, a low latency opportunity that we need to take action as soon as possible, right? So I have been using Booking for years, and I remember when I book a hotel, just book the hotel. Right now, actually Booking is a whole travel experience, right? So you book the hotel and you have tours, the flight, rent a car, and everything. So because Booking understand that they can take that opportunity to do more things, right? And more industries that are moving in that low latency experience direction because our customers are more digital, right? The banks, the applications, the SaaS. Now you don't take a taxi, you get boat, for example, okay? So everything is digital right now, which means we are able to capture those interactions compared to the traditional world that everything happens offline. Now the digital business, they have this opportunity, okay? We all know that we need this, but the reality is a little bit ugly, okay? We call the Frankenstein architecture, okay? So it's sustained by fear because everything can collapse, right? But the way the companies have been building AI system have been just a evolution for the traditional architecture. They didn't have the chance to re-architect. So they still have different frequencies of data, like Kafka. You may know Kafka, real-time data for systems, for interactions, but they still have batch ETL data, like medallion architecture, bronze, silver, gold, and it takes sometimes hours to get the gold data available to be consumed. Different storage, databases, vector search, lake houses, iceberg, you name it. And also a cache layer as well, of course, okay? And also different frequencies, different hopes, different systems that people need to maintain. Each one of these arrows, these interactions, it's a tax that people is paying. We need to glue these things together, and people need to maintain. That brings to our final analysis of these, companies, CIO and CTOs and CDOs and CXO, whatever. They have now this AI budget line, and they need to expand somehow. And IT systems, they need to find a solution, and they're basically trying to just integrate the AI in the current architecture. That brings to all those cost, right? Rack systems, they are basically providing stale data to agents. It doesn't make sense in the real business interaction digital platforms. We are not able to achieve our SLAs, basically, because we still have all those multi-stage pipelines. And also the team spend more time fixing, keep the lights on, firefighting with the data instead of actually bring value, right? That is what really matters and improve the business, okay? Let's take a step forward and let's understand how actually we can improve and modernize our architecture, right? So agents in real-time decisions, how they can work together. This is a marriage made in heaven, okay? We have Verica, powered by Apache Flink, an open source project that has been in the market for 11 years, actually, okay? There are a lot of companies that we have no idea that are using Flink today to do sub-second analytics like fraud detection, customer personalization, and so on, okay? It goes beyond to everything you know in terms of stream data and take decisions in real time. And also our convergent data layer, that is the TiDB, that you have not only the transactional data available for those agents, but also the analytics data and all the context available, okay? So let's deep dive a little bit of this architecture and how one stream, but with one storage, can serve all those pipelines together. So in the Verica side, as I mentioned, this is powered by Apache Flink, okay? Open source component that have been there, and this is widely adopted in many companies and many industry and countries. I like a lot the CEST approach because that lowered the barrier of adoption of those frameworks. They're really powerful, but if you need to go deep and develop in Java, for example, that requires, of course, an expertise and knowledge that most of the people, it takes time, right? It's not a 3 weeks vacation that you're able to learn, actually. It takes more than, 1 year sometimes, right? The learn curve. With Flink SQL or SQL ANSI, actually you are able to start to unlock in real time that data and connect. So what we can see here, it's a model DDL, how we create a model, right? That I get an input and I return back a output, right? That's what a model is, right? So I'm calling OpenAI and the model and all the parameters that I have. And that can be integrated in your insert into a TiDB database table with the chunks, right? And I'm calling this model during the execution, okay? This is powered by those functions, ML predict, vector search. You can call any OpenAI endpoints, so you can do a lot of things like classifications, with text embedding, and so on. Exactly once, that's really important if you work with transactional data. And of course, Flink should be one more component in your current data ecosystem, right? So you can easily integrate with 60+ connectors to Kafka, POSA, let me call them databases, FiOS, MongoDB, Elastic, TiDB, and all the ecosystem in your platform to get data in real time, or also batch data if needed as well. Okay, so this is the engine, the brain that will connect all the different pieces, all those business signals, and you're gonna generate those actions, right? But the memory is here, right? And the TiDB. So in the TiDB, what we can create is all those tables and repositories to actually store not only that have been used to our transactional database for business applications, CRMs, ERPs, and transactional systems, right? That we are pretty much comfortable in this distributed ecosystem and all the resilience that we can get from TiDB, but also have those native vector type that will be being collected, generated by those agents, right? So here, what we have is actually that memory and all that knowledge that we have built for all the organizations and our business entities. Okay. In that sense, all that Frankenstein, ugly, sustained by fear architecture that you have multiple hopes and the stages and pipelines to build an actual gold layer. We in this evolution, what we have is the shift left architecture, right? Or what I call the early ETL, right? Early data preparation. We can connect all those live events, the CDC, Kafkas, and so on, and we can immediately capture those business signals, trigger actions, preparations, and normalization, everything that we are comfortable with data, and integrate with TiDB to get context in different stages. I'm going to explain the next slide. That agent memory to take decisions. And then you take away decisions. So with the real-time data ready to be consumed, plus the memory and the context, you are able to improve the decisions. So you have enough aspects or enough context, right? Sorry, to take decisions. And then the decisions, it can be an API call, send an event, a push notification, and so on. And everything, of course, it should be a memory, should be updated, should be available throughout this pipeline. It's always a circle, right? You learn, and then you store, and will improve, and you continuously, generate that data. Those are the 4 memory layers that the agents or the real-time pipeline needs, okay? The first one, the 2 first we have here, they are refresh generated by the agents, right? So we have active sessions like I'm typing right now with ChatGPT and all that context that is part of one chat, let's say, okay? But also all the past interactions, all the features, past things that I have been doing on that. So it is more episodic, more historical, but also should be there because that helps us to learn more and more, right? So I actually, when we have a new project that is called Apache Flux, that is more kind of, let's say, Kafka with schema enforcement and everything. And I remember 6 months ago to start to search something about Flux, FLUSS, if you want to search about this project, in ChatGPT. And the information that I got was pretty basic. Right now, actually, it's pretty complete, right? So because it's constantly learned, right? Which means the active or the short-term memory starts to be part of the historical, and we have a full spectrum of that data. And also the semantic, okay, knowledge for the RAG systems. So here, where Verica can help you, right? Because we can take all those business signals in real time, enrich, and generate that knowledge base. And also procedural, TiDB, of course, with all the business transactional data that can be generated and stored in the database. But I think right now with all these, I think you have learned that Microsoft is not going to pay anymore. I think it's cloud, right? A license for cloud or OpenAI. Humans is getting back to work because AI is too expensive, right? So it looks like we finally have a kind of I don't remember the name of the company for a movie. I don't remember. Okay, sorry, but it looks like we are fighting against the robots, but it's in a different way, right? It's for more like a job position than like with for killing each other, right? So what do we have here? It's a path that Skynet. That's not the name of the company. Sorry. Okay. Yeah. So you are not fighting about Skynet anymore. It's about cloud and OpenAI, by the way. So we have all those signals, right? Business events and everything, and we need to take a decision. Do we need an agent that eventually is going to cost some tokens, right? And we need to store, or we can take a different auto path way that maybe complex event processing, base rules, actions, sub-second SLA, it's okay, right? I think we are still figuring it out. Most of the companies say, okay, it's everything here, it's one click and I have everything here. But I still have, I still believe that we have chance to take this auto path, or more like things that we know that works with our current tools. But regardless of the path we take, we always need to take an action, of course, like fraud detection or explain why the user, I'm not properly using my platform. That's LLM that can support us, of course, to explain this in a human way. We need to take an action and then, of course, always save that memory to improve and have the circle, okay? Great. But from MVPs to production, right? There's a lot of MVPs. I think the percentage of real AI initiatives that go in production is still really low. I think it's still below 50%, okay, which is we are not properly using or define our initiatives. But this is not a magic book that could say, okay, just apply this, it's going to work. But I think we have been learning more and more. For this real-time production readiness, we need a foundational aspect like recoverability or resilience. Of course, right? These are systems that are working parallel in a distributed system, which means if something fails, may fail. That's why you build distributed system, by the way, right? We need to recover, right? Checkpoints, TiDB, ACID transactions, and everything in that sense is going to help us to achieve this resilience check, right? Observability, of course, this is not a new topic. Everything should be, we can only improve what we actually measure, right? So in observability, we need to end-to-end. From data, from quality, from cost as well, everything should be in this foundational big check. And the operational side, keep the lights on. Durability, we need to make sure that our data will be there forever, and the agents and the transactional data and so on, everything should be in a way that we can recover throughout the years or in the way that really matters. I'm not sure if 10 years retention is already work with this kind of data, but in general, transactional data, financial data should be at least 5 or 10 years, depending on the country, and elasticity as well. So these systems can grow and add more capacity as soon as you need it, right? Or your demands require. You have the baseline. We start with the minimum, and then you start to add these as soon as you grow, right? So our FinOps teams, they'll be happy, right? Because we are properly using those resources out there, okay? With that TB, of course, this is really great because we can have agents branch, millions of agents, one single database working for you. You don't need to copy the data from the transactional to OLAP that has been happening for years. Maintain this is really hard. It requires an army, actually, in some companies. A new use case, it's a new role. It's not a new cluster, okay? Easy to maintain, single pane of glass, right? And also, it's linear. So you don't need to re-platform. You don't need to there's more agents, agent to agent initiative. You don't need to do this, okay? You don't need to reshard. So you just grow using the distributed and all the internal mechanisms of TiDB, okay? Production ready is really important, right? As I said before, exactly once. So Flink checkpoints and TiDB transactions can help it to cover this. So there's no partial, right? We make sure that we have received that acknowledge from the TiDB when we write data, and then we can continue, right? So and the Flink side as well, it has internal mechanisms to make sure that if a task manager fails, you can recover. Scheme evolution, unfortunately, data is constantly changing, right? Actually, that's really good, I think so. That's more work for us, of course, to maintain this. But scheme evolution is part of our life, right? A new column, a new feature to calculate and add to the customer or the employee entity, or enrich more our data systems, right? So this is really important to make sure that you have that flexibility to grow, right? Because today's requirement is not tomorrow's, right, requirement, and we need to evolve. We live in Europe. Sovereignty is something that really matters, okay? So make sure that everything runs in the context that you need. If you're adopting public cloud, great for you. But some companies, they highly regulated companies, they're still really restrictive to use some of the services, especially like SaaS services. But we see more of this in Europe. More companies want to take control, not only the stack, but also the infrastructure as well. And column level, of course, related to Europe, DORA, resilience, GDPR, all these kind of requirements that help us to have one more check with our, local regulations. Start small, but think big, right? I think that's one of our mantras. Connect to your business signal, data, transactions, interactions, compute, raw data. Those signals, unfortunately, they are not rich enough to use for to put in the context, to store in the context. So enriched data will be part of our compute all those raw events to meaningful events, to meaningful data. Then we can contextualize, to take a better decision, and then finally act, okay? Some companies, they start to figure out how to, build each one of those boxes here, okay? And of course, during these tomorrow morning or your next 3 days vacations you're gonna take, okay? You can think about this thing, right, to take home. Map your agent memory, right? Or do you need to build your agent strategy, or, it's not AI strategy, agent strategy. Try something, a reference architecture with TiDB Vertical in Flink, so we can work together, be here during the event, and we can, help you to build this in a proper way, this MVP. And start small, quick wins, hang fruits, right? Don't go for the, most complex architecture that maybe you need to talk to all the teams, and we cannot figure it out the proper return of investment of that product. Start small. I think there's a lot of things to test, make sure that you can build an MVP and, put in production. If it works, just scale. Resources not a big constraint your idea today, okay? So you just need to keep up and put that in production, okay? Sorry, I don't have a thank you slide, okay? But I really appreciate your time. I think this more like practical approach for real-time AI can help you to, envision the benefits, okay? Thanks so much.
Thank you, Alex. Very nice presentation. Very nice final point. What can I say? I'm really sad. Like, genuinely. Because we were preparing for this event over the last 3, 4, 5 months. I don't exactly remember. And now we are done with all our sessions, except for one. And some would say this is the most important session. I would argue with that, but it's a drinking session. So now we're going to have a happy hour and a panel discussion where we still have some chance to ask questions to our existing customers, how they are using TiDB, why they decided to use TiDB, what are the challenges. I will ask some questions that we received online during our session. But before we move out, I would like to thank all of you for participating in our very first EMEA SCaiLE event. It means the world to me. It means the world to our whole team. And again, thank you very much. And this applause are to you.